The universe, a swirling canvas of mystery and wonder, holds more secrets than we can fathom. From the intricate dance of planetary wonders to the bizarre anomalies that defy our understanding, the cosmos beckons us to explore deeper. What lies within the dark confines of distant galaxies, and how do alien worlds challenge the very essence of life as we know it? Join us today as we ignite your curiosity and embark on a quest for knowledge that may transform your understanding of the universe itself. There are several celestial phenomena that continue to baffle scientists today, even as our understanding of the universe advances. One of the most perplexing is dark matter. Despite making up approximately 27% of the universe, its true nature remains elusive. Dark matter does not emit light or energy, which makes it invisible and detectable only through its gravitational effects on visible matter. This mysterious substance holds the key to understanding the structure and behavior of galaxies, yet no one knows what it is composed of or how it was formed. Another intriguing mystery is dark energy, which accelerates the expansion of the universe. Dark energy accounts for nearly 70% of the universe and influences cosmic dynamics on a grand scale. Unlike matter, which clumps together to form galaxies and stars, dark energy seems to work in the opposite direction, pushing galaxies apart. This enigma raises fundamental questions about the fate of the universe and the forces that govern its structure. Fast radio bursts are also a phenomenon that has captured interest since their discovery. These short, intense bursts of radio waves travel across vast distances, and their origins are still unknown. Although some theories suggest they could be linked to neutron stars or even advanced extraterrestrial civilizations, concrete explanations elude researchers. The hunt for the source of these signals remains a prime focus in astrophysics. Lastly, the behavior of certain black holes presents another curious enigma. Particularly, supermassive black holes found at the centers of galaxies challenge our understanding. These giants can contain millions to billions of solar masses, but the precise mechanisms behind their formation and growth in the early universe are still unclear. Studying these celestial giants could unlock further secrets about galaxy evolution and the fundamental laws of physics. Each of these mysteries continues to fuel scientific inquiry and keeps our thirst for knowledge about the universe alive. Black holes play a crucial role in shaping the structure of surrounding galaxies, particularly at their centers. Most massive galaxies, including our own Milky Way, harbor supermassive black holes. These black holes exert immense gravitational forces which influence the motions of stars and gas in the galaxy. As objects spiral closer to the black hole, they are drawn in by its gravity, resulting in complex dynamics that can reshape the orbits of nearby stars. Moreover, the activity surrounding supermassive black holes can have a profound impact on the galaxy's evolution. When matter falls into a black hole, it often forms an accretion disk, a swirling mound of gas and dust that emits intense radiation. This radiation can heat up surrounding gas and drive powerful winds or jets that can disrupt star formation. These processes can alter the density of interstellar material and affect how stars are formed throughout the galaxy. Additionally, black holes are believed to influence the overall galactic morphology. The presence of a supermassive black hole correlates with the size of the galaxy's bulge. Larger bulges are typically found in galaxies hosting more massive black holes, suggesting a coevolution between black holes and their host galaxies. This relationship highlights how gravitational interactions and energy transfers shape the galactic environment over billions of years. As galactic structures evolve, the presence of these enigmatic entities leads to fascinating phenomena, including the potential creation of new star clusters and altering the paths of stellar orbits. The interplay between black holes and their host galaxies unveils a critical chapter in the story of cosmic evolution, confirming that these dark giants profoundly affect not only their immediate environments, but also the larger cosmic tapestry. Dark matter and dark energy are two of the universe's most fascinating mysteries, influencing the cosmos in ways that challenge our understanding of physics. Dark matter makes up about 27% of the total mass energy content of the universe, yet it cannot be observed directly. Its presence is inferred from the gravitational effects it has on visible matter. For example, when astronomers study galaxies, they find that the stars at the edges of these spirals rotate much faster than can be accounted for by the visible mass alone. This discrepancy suggests there must be additional mass present, which we term dark matter. On the other hand, dark energy is even more enigmatic, comprising about 73% of the universe. It is thought to be responsible for the accelerated expansion of the universe. Observations of distant supernovae revealed that not only is the universe expanding, but that the rate of this expansion is increasing. This phenomenon has led scientists to propose the existence of dark energy, a mysterious force pushing galaxies apart. The exact nature of dark energy remains one of the greatest puzzles in cosmology, with various theories positing it as a constant energy density in space or as a dynamic field. One of the intriguing aspects of dark matter is its potential interaction with ordinary matter. While it does not emit, absorb, or reflect light, leading to its elusive nature, certain theories suggest it may interact through weak forces. This raises the possibility that future experiments could lead to the discovery of dark matter particles, offering insights into the fundamental makeup of the universe. The ongoing search for dark matter is a testament to humanity's quest for understanding the cosmos and our place within it. Dark energy presents equally captivating questions about the fate of the universe. If dark energy remains constant, it could result in a scenario where galaxies continue to drift apart until they become isolated islands in an ever-expanding space. However, should dark energy change over time, it could lead to radically different outcomes for the universe. Understanding both dark matter and dark energy not only deepens our comprehension of cosmic history, but also poses profound implications for the very nature of reality itself. Despite the significant advances in technology and physics, detecting and understanding gravitational waves continues to be a formidable challenge. Gravitational waves are ripples in space-time produced by some of the most violent and energetic processes in the universe, such as colliding black holes or neutron stars. These waves are extraordinarily faint when they reach Earth, requiring incredibly sensitive instruments to observe them, like the Laser Interferometer Gravitational Wave Observatory, which utilizes laser beams to measure minute changes in distance caused by passing waves. The complexity of gravitational waves also contributes to the difficulty of detection and understanding. These phenomena stretch and compress space-time, affecting distances on a subatomic scale, which makes it essential for detection devices to maintain precision during measurements. Furthermore, the sources of gravitational waves produce signals that can vary widely in frequency and amplitude, necessitating sophisticated algorithms and data analysis techniques to decipher the vast amounts of information collected. Each detection is a unique event, and understanding their astrophysical origins demands intricate modeling of the systems involved. Compounding the challenge is the relatively recent nature of gravitational wave astronomy. Unlike electromagnetic waves, which have been studied for centuries, gravitational waves were first predicted by Albert Einstein in the early 20th century, and only recently have we begun to develop the means to detect them. As a young field of study, much of the underlying physics is still being explored, and there is still much to learn about how these waves propagate and interact with matter. As researchers continue to improve their detection techniques, the knowledge acquired from each event gradually builds our understanding. Each successful observation brings us closer to unlocking the mysteries of the cosmos, revealing insights into the nature of gravity itself, the formation of black holes, and the fundamental workings of the universe at large. Understanding these waves not only deepens our knowledge of astrophysics, but opens windows into moments in time that were previously unseen. Quasars, short for quasi-stellar objects, serve as brilliant beacons that illuminate the early universe's conditions and evolution. These exceptionally bright objects are powered by supermassive black holes at the centers of distant galaxies. As matter spirals into these black holes, it heats up and emits tremendous amounts of energy, often outshining entire galaxies. This extreme brightness allows astronomers to observe quasars that originated billions of years ago, giving us a glimpse into the universe at a time when it was still in its infancy. In studying quasars, scientists gain insights into the formation and growth of galaxies during the universe's early stages. The light radiated by these far-off objects carries vital information about the composition of the universe, including the presence of heavy elements. Observing the light from quasars, astronomers can identify the enrichment of intergalactic gas with materials forged in stars, highlighting the processes through which stars and galaxies evolved over time. This reveals intricate details about the interplay between black holes and their host galaxies. Moreover, quasars act as cosmic telescopes, revealing themselves as background objects whose light passes through the intervening cosmos. As this light travels across vast distances, it interacts with gas clouds and cosmic structures along the way, allowing scientists to study the characteristics of the universe during different eras. This interaction helps us understand the expansion of the universe and the distribution of dark matter, which shapes its large-scale structure. The study of quasars is crucial for piecing together the timeline of cosmic history. They are essential tools for probing the era of reionization, a period when the universe transitioned from opaque to transparent as the first stars lit up the dark cosmos. Through these extraordinary phenomena, quasars continue to enhance our understanding of the universe's origins, its evolution, and the complex relationships that exist within it. Exoplanets, or planets that orbit stars outside our solar system, present a fascinating puzzle for scientists trying to determine the potential for life beyond Earth. One of the most intriguing characteristics of exoplanets lies in their diverse conditions. For instance, some of these planets exist in what is called the hot Jupiter category, where they are gas giants located very close to their stars. The extreme temperatures and atmospheric conditions on these worlds challenge traditional notions of habitability, as the environments are likely inhospitable to life as we know it. Another significant factor is the range of planetary atmospheres observed. Some exoplanets have thick, toxic atmospheres filled with gases like sulfuric acid, while others may have very thin atmospheres or none at all. The composition and density of an exoplanet's atmosphere play crucial roles in regulating surface conditions, affecting temperature and pressure. These variations raise important questions about how life might adapt, if it could exist in such extremes, or how it might survive in conditions previously thought to be impossible. The concept of water worlds also complicates our understanding of habitability. These planets may have deep oceans covering their entire surfaces, creating environments quite different from the land and water mixtures on Earth. The challenges presented by these conditions include how such planets could establish the necessary chemical processes for life and whether the lack of landmass would hinder the development of complex organisms. Finally, the presence of exoplanets in the habitable zone of their stars does not guarantee that they can support life. Factors such as stellar radiation, magnetic fields, and geological activity can dramatically influence a planet's final suitability. As scientists continue to discover exoplanets capable of hosting water or exhibiting Earth-like features, they are prompted to rethink and expand the traditional definitions of habitability, leading to new discussions about what life might look like across the universe. Extreme weather patterns on gas giants like Jupiter and Saturn are strikingly different from those on terrestrial planets such as Earth and Mars, primarily due to their composition and atmospheric dynamics. Gas giants are composed mostly of hydrogen and helium, with thick atmospheres that can extend thousands of kilometers deep. This leads to intense, long-lasting storm systems. For example, Jupiter's Great Red Spot has persisted for over 300 years, showcasing a colossal storm that is larger than Earth itself. In contrast, terrestrial planets have solid surfaces and thinner atmospheres, which limits the scale and duration of storms. Earth, for instance, experiences weather patterns driven by its oceans and seasons, leading to phenomena like hurricanes and thunderstorms that are transient in nature. These storms typically last days or weeks, influenced by factors such as landmass, temperature variations, and atmospheric pressure changes. Gas giants also have complex wind patterns that can create astonishing weather phenomena, such as the supersonic winds observed on Jupiter, which reach speeds of around 400 miles per hour. The atmospheric layers of gas giants can circulate in distinct bands, resulting in fierce storms and turbulence at the interfaces of these bands. The lack of a solid surface allows for the formation of massive systems that can interact over vast distances. The distinct differences stem from their unique characteristics. While terrestrial planets face weather that is often localized and affected by their geography, gas giants display extreme storms that are driven by massive atmospheric forces. The scale and intensity of these patterns offer a glimpse into the dynamic nature of our solar system, revealing how different environments can shape weather in fascinating ways. Venus, often referred to as Earth's twin due to its similar size and proximity, presents an intriguing set of mysteries that extend well beyond its scorching surface. This planet is enveloped in a thick atmosphere composed primarily of carbon dioxide, with sulfuric acid clouds that trap heat in a runaway greenhouse effect. Surface temperatures soar to around 800 degrees Fahrenheit, making it the hottest planet in the solar system. This extreme environment raises questions about the potential for any form of life to have existed there, particularly in its ancient past when conditions may have been different. The exploration of Venus has revealed features that hint at a more temperate history. Geological formations such as ancient riverbeds and mountains suggest the presence of liquid water long ago. Scientists believe that, billions of years in the past, Venus may have had a much milder climate that could have supported microbial life. If this was the case, understanding the planet's transformation into the harsh environment we see today is crucial. Evidence of volcanic activity on Venus points to geologically active processes that might have altered its surface and atmosphere over time. Further complicating the search for answers is the presence of phosphine gas detected in the upper atmosphere. Phosphine on Earth is primarily produced by microbial life, prompting speculation about the possibility of living organisms existing in the clouds of Venus, where conditions are less extreme. However, this remains a contentious observation, with ongoing debates in the scientific community regarding its origins. The argument hinges on whether phosphine could be produced by non-biological processes, or if it truly signifies the presence of life. As robotic missions continue to study Venus, secrets about its surface and atmospheric dynamics come to light. The prospects of uncovering evidence of past life or even current microbial life keep attracting attention. Each discovery not only deepens our understanding of Venus, but also shapes our perception of what life could potentially look like, especially in environments previously considered too inhospitable. The allure of Venus lies in its mysteries, promising to expand our knowledge of planetary science and life's adaptability in varied conditions. Scientists utilize an array of sophisticated techniques and technologies to gather information about distant planets, often located light years away from our home planet. One of the primary methods is through the use of powerful telescopes, both ground-based and space-based. These telescopes capture light from distant stars and planets, allowing scientists to analyze this light to determine various characteristics of those celestial bodies, including their composition and temperature. Among the most significant discoveries of exoplanets, or planets outside our solar system, has been achieved through the transit method. This technique involves monitoring the brightness of stars for periodic dips in light. Such dips indicate that a planet is passing in front of a star from our point of view. By determining how much light is blocked, scientists can estimate the size of the exoplanet. Additionally, the length of the transit reveals the planet's orbit, providing insights into its distance from the star and potential habitability. Another powerful tool for planetary observation is the radial velocity method, which examines the wobble of a star caused by the gravitational pull of orbiting planets. As a planet circles its star, it exerts a gravitational force that causes the star to move slightly in response. By measuring changes in the star's light spectrum, specifically shifts in the wavelengths caused by the Doppler effect, scientists can gather data about the mass and orbit of the planet. Astrobiologists are also keen on analyzing atmospheric compositions through a method known as spectroscopy. When a star's light passes through a planet's atmosphere, certain wavelengths of light are absorbed by different gases. This absorption creates unique patterns that can be deciphered to identify the atmospheric components, including potential indicators of life. Each of these methods relies on cutting-edge technology and international collaboration, slowly unraveling the mysteries of our vast universe. The discovery of water on Mars has been a groundbreaking achievement in our quest to understand the planet and its potential to harbor life. Water is essential for all known forms of life on Earth, and its presence on Mars raises substantial questions about whether life ever existed there or could currently exist in some form. Scientists have detected water in various forms, including ice at the polar caps and briny liquid water flows in some crater locations, indicating that Mars does still possess the essential ingredient for life. The presence of water dramatically alters our perspective on the history of Mars. Once thought to be a dry, barren world, evidence suggests that ancient Mars may have had a much more Earth-like environment with rivers, lakes, and possibly even oceans. This opens the possibility that microbial life may have thrived in the past. If life existed on Mars, it could inform us about the conditions necessary for life to emerge, providing important insights into the possibilities of life elsewhere in the universe. Studying Mars' water resources also carries practical implications for future exploration missions. Any human-crewed missions to Mars will need to utilize local resources to support life, and water is a critical element for sustaining astronauts during their journeys. If we can confirm the availability of accessible water sources, this could make prolonged stays on Mars more feasible and less reliant on resupply from Earth. Furthermore, the search for water on Mars is deeply intertwined with our scientific endeavors regarding planetary evolution and climate change. Understanding how water has cycled on Mars can offer clues about how similar processes work on Earth and other celestial bodies. This knowledge not only enriches our understanding of Mars, but also enhances our comprehension of our own planet and the broader universe. The Hubble Space Telescope has revolutionized our understanding of the universe since its launch in 1990. Among its most astonishing discoveries is the observation that the universe is not just expanding, but doing so at an accelerating rate. The telescope captured this phenomenon by measuring the light from distant supernovae, revealing that a mysterious force, dubbed dark energy, is driving this acceleration. This finding has reshaped cosmological theories and deepened the mystery surrounding the composition of the universe. Another remarkable discovery is the detailed analysis of galaxy formation and evolution. Hubble has unveiled that galaxies are far more diverse than previously thought, identifying various shapes, sizes, and colors. Observations of the galaxy cluster Abell 370, for example, revealed arcs of light created by gravitational lensing, allowing astronomers to see objects previously hidden from view. This phenomenon not only highlights Hubble's capability, but also provides insights into the gravitational pull of massive structures in space. Hubble has also captured breathtaking images of distant exoplanets, offering valuable data about their atmospheres and compositions. It identified the presence of water vapor in the atmosphere of an exoplanet located several hundred light-years away, suggesting that conditions necessary for life could exist beyond our solar system. This breakthrough has sparked excitement and optimism in the search for extraterrestrial life. Additionally, the telescope has provided profound insights into the life cycles of stars. Hubble's imagery of various nebulae has illustrated processes such as star formation and supernova explosions in vivid detail, allowing scientists to study the life cycle of stars from birth to death. These observations have deepened our understanding of how elements are forged in stars and later dispersed throughout the cosmos, contributing to the complex web that forms galaxies and potentially supports life. Cosmic rays play a significant role in enhancing our understanding of the universe. These high-energy particles, primarily originating from supernovae and other energetic astronomical phenomena, travel through space and occasionally collide with the Earth's atmosphere. When they do, they create showers of secondary particles that can be detected by various instruments on the ground and in space. This interaction opens a window into understanding the fundamental processes of astrophysics and the nature of cosmic events. The study of cosmic rays allows scientists to explore not only the origins and acceleration mechanisms of these particles, but also the conditions found in distant celestial environments. By analyzing the energy and composition of cosmic rays, researchers can glean insights into the composition of the universe itself, including the distributions of elements and the presence of exotic particles. This information is critical for formulating theories about the evolution of galaxies and the interstellar medium. Furthermore, cosmic rays contribute to ongoing research in particle physics. When cosmic rays collide with atoms in our atmosphere, they produce a cascade of particles that can be studied to investigate fundamental questions about matter and energy. This intersection of astrophysics and particle physics has led to the development of advanced technologies and methods, reinforcing our understanding of the universe at its most fundamental level. Additionally, cosmic rays pose intriguing questions regarding their impact on life on Earth. While most of these high-energy particles are shielded by our atmosphere, some can penetrate to the surface. The extent of cosmic radiation exposure influences everything from airline travel to potential future human exploration of Mars. Undertaking this research allows us to fully grasp not only the dynamics of outer space, but also their implications for life on our planet. Rogue planets, often described as the mysterious wanderers of the cosmos, are unique celestial objects that do not orbit a star. Instead, they drift through the vast darkness of space, unattached to any solar system. What makes them particularly unusual is that they can vary significantly in size, composition, and temperature. Some may be akin to gas giants like Jupiter, while others could be more Earth-like in their rocky nature. Their ability to exist in the cold vacuum of space, far from any star's warmth, challenges our understanding of planetary formation and stability. These planets can be formed in a variety of ways. Many researchers believe they might originate as normal planets within a solar system, but are ejected due to gravitational interactions with larger bodies or competing planets. Others may come into existence in the protoplanetary disks surrounding young stars, but instead of settling into an orbit, they could escape the gravitational pull of their star. This process grants them the title of rogue, and it highlights the dynamic nature of planetary systems. Rogue planets can be found in diverse regions of space. Some may roam within the Milky Way galaxy, and estimates suggest there could be billions of such planets in our cosmic neighborhood. Scientists have speculated that rogue planets might also exist in structures like the Oort cloud, which is a theoretical cloud of icy bodies surrounding our solar system far beyond the orbit of Neptune. Additionally, rogue planets could conceivably drift between galaxies, adding to the perplexity of the universe's architecture. The search for rogue planets is ongoing, as they are notoriously difficult to detect. Astronomers often rely on indirect methods, such as observing the gravitational effects of these planets on surrounding objects or looking for their faint thermal emissions. The study of rogue planets not only expands our understanding of planetary formation, but also raises intriguing questions about the potential for life in these isolated worlds. As research progresses, these enigmatic planets continue to inspire curiosity about our galaxy and the countless mysteries it holds. Natural satellites, commonly known as moons, play significant roles in shaping the behavior of their host planets in various ways. One of the most critical influences is through gravitational interactions. For instance, the gravitational pull exerted by a moon can affect tidal forces on the planet, leading to predictable rise and fall of ocean levels. This phenomenon is especially pronounced on Earth, where the moon's gravitational force creates daily tides, influencing marine ecosystems and coastal environments. Additionally, moons can stabilize the axial tilt of their host planets. The Earth's axial tilt is maintained largely because of the stabilizing influence of the moon. A stable axial tilt helps regulate climate patterns, as it affects how sunlight is distributed across the planet throughout the year. This stability is crucial for supporting diverse ecosystems and maintaining life as we know it. Without such a satellite, a planet's axis could wobble dramatically, leading to extreme climatic shifts. Moreover, certain moons can impact geological activity on their host planets. For example, the gravitational tug from Jupiter's large moon, Io, creates intense tidal heating. This process generates enormous volcanic activity on Io, making it the most geologically active body in the solar system. Similar mechanisms could be at play on other planets, where the gravitational interaction with their moons results in geological changes. Lastly, satellites can also contribute to the evolution of a planet's atmosphere. For instance, the interaction between a moon's gravity and the solar wind can influence how atmospheric particles are retained or lost. Such dynamics play an essential part in the atmospheric conditions over billions of years, ultimately affecting the potential for life on those planets. The relationship between planets and their moons is a compelling example of how celestial bodies can shape each other's destinies across the cosmos. While the moon has been extensively studied since the Apollo missions, many hidden features remain unexplored and hold tantalizing secrets about its formation and history. Scientists have observed various geological formations through telescopes and spacecraft, but numerous areas still await detailed examination. For instance, the far side of the moon presents a unique frontier. Unlike the near side that faces Earth, the far side features an entirely different landscape, including the largest and oldest impact basin in the solar system, known as the South Pole Aitken Basin. Lunar lava tubes, formed by flowing molten rock, are another intriguing aspect yet to be thoroughly investigated. These tunnels could provide insights into volcanic activity on the moon and offer potential shelters for future astronauts. Some of these tubes are large enough to house entire bases, protecting occupants from harsh radiation and extreme temperatures. The exploration of these features could reveal the moon's volcanic past and present, enriching our understanding of its geological processes. The presence of water ice in permanently shadowed craters at the lunar poles presents another exciting area of research. Although some radar observations suggest the existence of ice, confirming its quantity and accessibility is crucial. Such findings could support the notion of sustainable lunar habitats and fuel for future missions deeper into space. New missions, like those from various countries and private companies, aim to investigate these regions directly, likely leading to groundbreaking discoveries. Additionally, the moon's exosphere, although extremely thin, contains trace gases and unique elements. Analyzing these gases could offer clues about the moon's formation and evolutionary history. Continued exploration, including landings and sample returns, promises to unveil more about our lunar neighbor, ensuring that even in our backyard there is still much to learn. The Andromeda galaxy, known as M31, captivates astrophysicists and enthusiasts alike due to its proximity and sheer scale. It is the nearest spiral galaxy to our own Milky Way, located approximately 2.5 million light-years away. This closeness allows astronomers to study its structure, star formation, and dynamics in remarkable detail, providing insights into the evolutionary processes that shape galaxies. One of the most compelling aspects of Andromeda is its size. It is over 200,000 light-years in diameter, more than twice the size of the Milky Way, and hosts approximately 1 trillion stars. This immense population offers a unique opportunity to observe different stellar types, including massive stars that burn bright and quickly, as well as older, cooler stars that illustrate various stages in galactic evolution. Astronomers are particularly intrigued by the fate that awaits the Milky Way and Andromeda. Predictions indicate that the two galaxies are on a collision course, projected to meet in about 4 billion years. This potential merger will lead to new star formation and the eventual creation of a larger elliptical galaxy. The study of Andromeda therefore provides critical data about galaxy interactions, helping scientists understand how such events influence the architecture and future of galaxies across the universe. Additionally, Andromeda's extensive collection of satellite galaxies showcases a complex gravitational ecosystem. These smaller galaxies are vital for understanding the characteristics of dark matter, which makes up a significant portion of the universe's mass but remains elusive. The interplay between Andromeda and its satellites presents an exciting opportunity to explore the hidden mechanics of cosmic structure and behavior, making it an ever-relevant focal point in astrophysical research. When galaxies collide, they undergo a complex process that leads to dramatic transformations over millions of years. Initially, two galaxies may pass through one another, their stars essentially unharmed due to the vast distances between them. However, as they interact through gravitational forces, their shapes begin to distort, leading to the formation of tidal tails, streamers of stars and gas that extend into space. Over time, these interactions can pull the galaxies closer until they eventually merge into a single, larger galaxy. This merging process can trigger bursts of star formation, known as starbursts, as clouds of gas collide and compress. Such intense star formation can create new stars at a rate significantly higher than the typical rate seen in galaxies that are not experiencing collisions. As new stars ignite, they illuminate the surrounding gas, producing a brilliant display of light. This phenomenon not only transforms the physical structure of the galaxies involved, but also significantly alters their chemical compositions as new elements formed in stars are released back into space. The aftermath of a collision can lead to the formation of elliptical galaxies, which have a much smoother appearance compared to their spiral counterparts. Studying these evolving galaxies provides scientists with critical insights into the life cycle of galaxies and the role of dark matter, which influences the dynamics of gravitational interactions. Many of the galaxies that we currently observe in the universe have likely undergone one or several merger events, shaping their unique characteristics. Colliding galaxies also present fascinating mysteries. For instance, the fate of the stars within these galaxies can be unpredictable. Some stars may be propelled outward into intergalactic space, while others become intimately intertwined with their new galactic environment. Additionally, questions about the role of supermassive black holes at the centers of galaxies raise intriguing possibilities. When galaxies merge, their black holes also draw closer, potentially leading to spectacular interactions. Observations of these phenomena continue to challenge our understanding of cosmic evolution and hint at deeper cosmic relationships yet to be uncovered. Barred spiral galaxies possess distinct features that set them apart from other galactic structures. One of their most notable characteristics is the presence of a central bar-shaped structure, which stretches across the nucleus and extends out to the spiral arms. This bar acts like a gravitational anchor, influencing the motion of stars and gas within the galaxy. As a result, the spiral arms often appear more tightly wound compared to those in regular spiral galaxies. The formation of these bars is believed to arise from the dynamics within the galaxy. Over time, gravitational interactions and the rotation of the galaxy can lead to instabilities that create this elongated formation. This central bar configuration facilitates the flow of gas towards the core, sparking increased star formation activity in that region. Consequently, barred spiral galaxies often exhibit a higher rate of star formation than their non-barred counterparts. Another intriguing aspect of barred spiral galaxies is the diversity of their structures. They come in various sizes and can feature different levels of brightness in their spiral arms. Some may have very pronounced bars, while others may present more subtle variations. This variety gives astronomers a unique opportunity to study the dynamics and evolution of galaxies, providing insights into how cosmic forces shape their development. Barred spiral galaxies are also important for understanding the evolution of galactic ecosystems. Their bars facilitate the redistribution of matter and energy, fostering various star formation events and influencing the overall evolution of the galaxy over billions of years. This complex interplay of gravitational forces and stellar evolution highlights the dynamic and ever-changing nature of the universe we inhabit. Starburst galaxies are a fascinating class of galaxies that stand out due to their exceptional rate of star formation. While typical galaxies form stars at a steady pace, starburst galaxies can create new stars at a rate several times greater than what we see in more conventional environments. This rapid star formation can lead to the birth of thousands of stars each year, often packed into dense regions that illuminate the galaxy with vibrant light. The explosive activity in starburst galaxies is primarily driven by the interactions between galaxies. When two or more galaxies collide or come very close to each other, their gravitational forces can disturb the gas and dust within them, triggering a surge of star formation. This phenomenon is so intense that it often results in the creation of massive stars that live fast and die young, leading to supernova explosions that can further affect their surroundings. In addition to galactic collisions, the presence of significant amounts of gas is crucial for these galaxies. The dense clouds of gas can collapse under their own gravity, forming millions of new stars in the process. A starburst event can last from a few million to several 100 million years, during which the activity can dramatically alter the galaxy's structure and appearance, making it look irregular and chaotic compared to the more orderly disks of typical galaxies. As starbursts progress, the feedback from newly formed stars, particularly massive ones, can blow out gas and dust, influencing the evolution of the galaxy itself. This outflow can enrich the surrounding intergalactic medium with heavy elements and can quench the star formation process within the galaxy as it uses up its available gas supplies. The dynamic life cycle of starburst galaxies provides astronomers with valuable insights into the birth and evolution of galaxies throughout the universe. Supermassive black holes are fascinating entities that exist at the centers of most, if not all, large galaxies, including our own Milky Way. These gigantic black holes can weigh millions to billions of times more than our Sun. Their presence significantly influences the formation and evolution of galaxies in several ways. As galaxies developed, supermassive black holes likely formed from the merging of smaller black holes and the accumulation of gas and stars. The growth of these black holes can impact their host galaxies through gravitational forces, affecting the motion of stars and gas in their vicinity. This gravitational influence can create a dynamic environment where star formation is either encouraged or inhibited, altering the overall structure and development of the galaxy. Moreover, when matter falls into a supermassive black hole, it generates immense energy and emits powerful jets of radiation and particles. This process can produce significant feedback effects that can heat and expel gas from the surrounding galaxy, thereby regulating star formation. The balance between star formation and the energy produced by the black hole's activity plays a critical role in determining the lifetime and evolution of galaxies. The relationship between supermassive black holes and their host galaxies is often described as a co-evolutionary process. As galaxies grow and evolve, so too do their central black holes, and vice versa. This interconnected development highlights a symbiotic relationship where the black hole influences the galaxy's fate, while the galaxy provides the materials necessary for the black hole to grow. This intricate dance between galaxies and their supermassive black holes continues to be an essential area of study in understanding the cosmos. Cosmic inflation theories provide a fascinating explanation for the remarkable uniformity observed throughout the universe. This uniformity refers to the consistent distribution of matter, energy, and the cosmic microwave background radiation across vast distances, which seems surprisingly homogeneous despite the billions of light-years involved. The central idea of cosmic inflation is that in the very early moments of the universe, just after the Big Bang, it underwent a rapid and exponential expansion. This brief period of inflation stretched out the fabric of space-time dramatically, causing regions that were initially close together to become far removed from one another. During this expansion, tiny quantum fluctuations which existed on a minuscule scale were amplified to cosmic proportions. As a result, the seeds of galaxies and large-scale structures emerged uniformly across the universe. This inflationary process allowed different regions, now separated by enormous distances, to have similar physical properties. While they may never have directly interacted with one another after the inflationary period, their shared origins explain why we observe similar conditions today. The uniform distribution of the cosmic microwave background radiation serves as strong evidence for this theory, as it shows a near-perfect equilibrium across the sky, revealing that the universe's expansion did not lead to diverse conditions as one might expect. Furthermore, inflation theories suggest that the rapid expansion helps solve several other puzzles related to the early universe, such as the flatness problem and the horizon problem. These challenges raised questions about how different regions of the universe could have the same temperature and density without any apparent means of communication. Inflation not only addresses these issues, but reinforces our understanding of why the universe appears so uniform on a grand scale. Multiverse theories suggest that our universe might be just one of many that coexist, each potentially having different physical laws and constants. This idea vastly expands our understanding of reality, challenging the notion that our universe is unique. Instead, it opens up the tantalizing possibility that there are countless variations of existence, each with its own set of circumstances and outcomes. One compelling implication of multiverse theories is how they redefine the concept of probabilities. In a multiverse scenario, every possible outcome of every event could potentially occur in some universe. This could mean that alternate realities exist where historical events unfolded differently, or where life forms developed in ways unimaginable to us. Such variations compel us to reconsider what we deem normal or possible in our own universe. Additionally, multiverse theories intersect with concepts in quantum mechanics. For instance, the many worlds interpretation suggests that every time a quantum event occurs, the universe splits into branches, creating distinct realities for each possible outcome. This interpretation could fundamentally alter our understanding of fate, free will, and the interconnectedness of all things in our universe. As scientists explore these theories, they confront profound philosophical questions about existence, knowledge, and the nature of reality itself. While multiverse theories remain speculative, they encourage both scientists and thinkers to envision a broader scope of existence, prompting debates not just about the nature of our universe, but the essence of reality. Recent discoveries regarding antimatter have unveiled profound implications for how we understand the universe. Antimatter, the elusive counterpart to regular matter, is composed of particles that have the same mass as their matter counterparts, but possess opposite charges. For instance, while electrons have a negative charge, positrons, beta particles of antimatter, carry a positive charge. The existence of antimatter raises crucial questions about the origins and composition of the universe. One significant area of research is the apparent imbalance between matter and antimatter that exists in our universe. The Big Bang theory posits that equal amounts of matter and antimatter should have been created. However, observations indicate a striking dominance of matter, leading to the question, where did the antimatter go? This enigma has prompted experiments, such as those conducted at particle accelerators, to investigate the properties of antimatter and search for potential differences in behavior between matter and antimatter. These studies aim to uncover what might have caused this imbalance, which could reshape our understanding of cosmic evolution and the fundamental laws of physics. Moreover, researchers have explored the possibility of antimatter containing unique forms of energy. For example, when matter and antimatter encounter one another, they annihilate, releasing a vast amount of energy in the process. This physical property opens discussions on theoretical applications, such as utilizing antimatter as a potential energy source or for propulsion systems in advanced spacecraft. While these ideas currently reside in the realm of speculation, the scientific investigation into antimatter provides a fertile ground for future technologies and innovations that could transform our capabilities in space exploration. Recent experiments have aimed to capture and study antihydrogen, the simplest atom of antimatter, in order to delve deeper into its properties. If it can be shown that antihydrogen behaves differently from regular hydrogen, it may lend credence to the theories attempting to explain the asymmetry between matter and antimatter. As these investigations continue, they hold the potential not only to answer age-old questions, but also to open new pathways of inquiry in cosmology, redefining our understanding of the universe at its most fundamental level. The cosmic microwave background radiation is often regarded as a cornerstone of modern cosmology. This faint glow of radiation fills the universe and serves as a snapshot of the infant cosmos, occurring just over 380,000 years after the Big Bang. At this time, the universe had cooled sufficiently for protons and electrons to combine into hydrogen atoms, allowing photons or light particles to travel freely. This event marked the transition from a hot, opaque state to the clear universe we observe today. Detecting this radiation offers profound insights into the early universe. The cosmic microwave background, often abbreviated as CMB, provides a wealth of information about the conditions that prevailed shortly after the Big Bang. It shows how matter was distributed, which in turn has implications for the formation of galaxies and large-scale structures. The tiny fluctuations in its temperature correspond to density variations in the early universe, portraying the seeds of galaxies yet to form. Moreover, the cosmic microwave background serves as a tool for testing cosmological models. By analyzing the properties of the CMB, scientists can determine critical parameters of the universe, such as its age, composition, and rate of expansion. For instance, measurements from satellite missions like the Wilkinson Microwave Anisotropy Probe and the Planck Observatory have produced highly precise data that refine our understanding of dark energy and dark matter. The existence and characteristics of the cosmic microwave background provide strong evidence for the Big Bang theory, effectively reinforcing our understanding of how the universe has evolved over billions of years. It is a tangible remnant of the early universe, allowing scientists to peer back in time and unravel the mysteries of cosmic history. This cornerstone of cosmology continues to be a rich field of research and exploration, prompting questions that push the boundaries of our knowledge and understanding. Observable variables are critical tools for scientists as they seek to understand the origins of the universe. These variables include phenomena such as cosmic microwave background radiation, the distribution of galaxies, and the abundance of light elements like hydrogen and helium. Each of these aspects provides crucial data that informs theoretical models about how the universe began and evolved. For instance, cosmic microwave background radiation serves as a relic of the early universe, dating back to just after the Big Bang. By studying its temperature fluctuations, scientists can glean information about the universe's early conditions and the processes that led to its current structure. The patterns observed in this radiation act as a cosmic fingerprint, enabling researchers to test different theories about the universe's expansion and its overall fate. Likewise, the distribution of galaxies across vast distances reveals much about the universe's evolution. By examining how galaxies cluster and the rate at which they move apart, scientists can infer the dynamics of cosmic expansion and the influence of gravity. This observational data supports the prevailing model of an expanding universe, originally proposed by astronomer Edwin Hubble, who discovered that distant galaxies are moving away from us, suggesting the universe itself is growing larger over time. Furthermore, the abundance of light elements in the universe offers vital clues about the processes that occurred in the very first moments after the Big Bang. Theories of nucleosynthesis explain how certain elements were formed as the universe cooled. The observed ratios of these elements align closely with predictions made by Big Bang nucleosynthesis models, thereby lending further support to theories about the universe's origins. By piecing together these observable variables, scientists continue to build a clearer and more comprehensive picture of how our universe came to be. Exoplanets are planets that orbit stars outside our solar system, and some of these distant worlds inhabit extreme environments that challenge our conventional ideas about life and habitability. For instance, one notable exoplanet is WASP-72b, a gas giant located about 40 light-years from Earth. It experiences scorching temperatures exceeding 1,000 degrees Celsius, resulting in a permanent state of a bloated atmosphere filled with metallic clouds. Understanding how life could survive in such sizzling conditions raises questions about the resilience of life as we know it. Another fascinating example is TRAPPIST-1d, which is part of a system containing 7 Earth-sized planets. While it resides in the habitable zone, its atmosphere is thought to be extremely dense, potentially leading to immense surface pressures. This world likely faces unpredictable weather systems, which could be unlike anything found on Earth. Traditional models of astrobiology usually stem from our planet's experiences, which generally foster life within a narrow range of temperatures and pressures. However, extreme worlds encourage scientists to broaden their understanding of what may constitute a habitable environment. Then there is Kelt 11b, a planet that orbits a star about 500 light-years away. This gas giant has a temperature so high that it may possess clouds made of molten glass, driven by potent winds. Such raging conditions force astrobiologists to reconsider the types of biological processes that could persist under such intense physical forces. Perhaps life could adopt forms that are fundamentally different from those on Earth, thriving in environments dominated by thermal extremes and crushing atmospheric pressure. Investigating these extreme exoplanets offers an exciting new frontier in understanding life's potential beyond our world. By expanding the parameters of habitability, researchers and scientists challenge the long-held beliefs of traditional astrobiology. This exploration ignites curiosity and highlights the possibility that life may exhibit a diversity greater than we ever imagined, thriving in conditions vastly different from those we experience on our planet. The hunt for extraterrestrial intelligence is experiencing a profound transformation thanks to advancements in technology. Modern telescopes equipped with powerful sensors can now observe distant exoplanets, some of which lie in the so-called habitable zone, a region where conditions might support life. For instance, the James Webb Space Telescope offers unprecedented views of distant worlds, allowing scientists to analyze their atmospheres for signs of chemicals associated with life, such as oxygen or methane. Additionally, artificial intelligence is playing a pivotal role in processing the vast amounts of data generated by these observations. Machine learning algorithms can sift through signals from space, identifying patterns that human analysts may overlook. This approach heightens the chances of detecting unusual signals, which could potentially indicate extraterrestrial technology. The increasing sophistication of signal processing methods enables researchers to filter out cosmic noise and focus on what might really matter. Radio astronomy continues to be a cornerstone in the search for intelligent life. Projects like the Search for Extraterrestrial Intelligence, or SETI, are expanding their reach, utilizing arrays of antennas that can observe multiple frequencies at once. This capability allows researchers to scan the sky more efficiently, searching for artificial signals that stand out from natural cosmic background noise. The collaboration between various SETI initiatives worldwide enhances the search by pooling resources and expertise. Moreover, the rise of citizen science projects empowers the public to engage in the search. Many initiatives allow enthusiasts to analyze radio signals or satellite images, providing vital additional eyes in the quest for understanding our universe. This collaborative effort not only broadens the pool of potential discoveries, but also fosters a shared sense of curiosity about the cosmic neighborhood we inhabit. Together, these technological advances and collective efforts redefine humanity's quest to answer the age-old question, are we alone in the universe? The atmospheres of exoplanets, those planets located outside our solar system, offer tantalizing clues about their potential to support life. By analyzing the composition of these atmospheres, scientists can understand the chemical processes occurring on the planet and potentially the presence of life. When searching for signs of habitability, researchers often look for molecules such as oxygen, methane, and carbon dioxide. These gases can indicate active biological processes, as they tend to exist in a delicate balance that life can influence. For instance, the detection of oxygen in an atmosphere could suggest that there are living organisms producing it through photosynthesis. However, oxygen alone is not sufficient proof of life. The presence of methane alongside oxygen becomes particularly intriguing. In Earth's atmosphere, these two gases exist in dynamic equilibrium, but they can also indicate biological activity. If both gases are found together on an exoplanet, it could imply that a system capable of supporting life is at play, as methane is typically short-lived in the presence of oxygen without a continuous source. Additionally, the presence of other compounds like water vapor can also elevate a planet's profile as a candidate for life. Water is often regarded as essential for life as we know it, so its detection could point to conditions that might support biological processes. The unique conditions within a planet's atmosphere, such as temperature, pressure, and the presence of clouds, play a vital role in determining its climate and overall ability to sustain life. Ultimately, understanding the atmospheres of these distant worlds not only helps scientists gauge their habitability, but also informs us about the diverse forms life could take beyond Earth. Each discovery adds another piece to the puzzle of what constitutes a habitable environment, expanding our understanding of life's possibilities in the universe. Exploring Earth's atmosphere provides valuable insights that are crucial for our understanding of alien environments. One prominent lesson is the importance of the balance between various gases. On Earth, the mixture of gases like nitrogen, oxygen, and carbon dioxide supports life as we know it. This balance is delicate. Even slight changes can lead to significant consequences, such as climate change. By studying atmospheric compositions on distant planets or moons, scientists can seek analogous environments that might be capable of supporting life. Another lesson is the significance of pressure and temperature. Earth's atmosphere protects us from harmful radiation and helps regulate temperature, creating a stable environment. When exploring other planets, scientists must consider how atmospheric pressure and temperature affect the viability of potential habitats. For instance, Venus has a dense atmosphere with extreme temperatures, which presents challenges for any form of life when compared to Earth's mild conditions. Understanding these dynamic factors enables researchers to prioritize environments that may be conducive to life. Additionally, Earth's atmosphere teaches us about the processes of erosion and weathering, which shape planetary surfaces. These processes influence climate and habitability. Studying how wind, rain, and temperature variations affect Earth's landscape helps scientists predict similar processes on other celestial bodies. For example, examining ancient river valleys or sediment deposits on Mars can reveal past climatic conditions, providing clues to its habitability and the potential for finding signs of past life. These lessons from Earth's atmosphere not only guide our search for habitable environments beyond our planet, but also bolster our efforts to better understand climate change and environmental stewardship on Earth itself. Each discovery strengthens our perspective, illuminating the interconnectedness of atmospheres across the cosmos and their capacity to sustain or challenge life. Scientists utilize a combination of advanced technology and intricate methods to identify signs of biological activity on distant planets. One of the primary tools in this exploration is spectroscopy. By analyzing the light that passes through a planet's atmosphere, scientists can detect the presence of specific gases. Certain gases, such as oxygen and methane, are strongly associated with life on Earth. When these gases are found together in significant quantities, they hint at potential biological processes. Telescopes, especially those situated in space like the Hubble Space Telescope and the James Webb Space Telescope, play a crucial role in this endeavor. These instruments can capture light emitted or reflected by distant planets, providing vital clues about their atmospheric composition. The James Webb Space Telescope, with its infrared capabilities, allows astronomers to peer into the atmospheres of exoplanets, revealing details that were previously unimaginable. Additionally, scientists examine planets located in the so-called habitable zone, the region around a star where conditions may allow for liquid water, which is essential for life as we know it. The search often focuses on planets that share similar characteristics with Earth, including size, temperature, and the presence of water. This selective approach increases the likelihood of finding biological markers. As technology advances, scientists are developing more sophisticated models to understand how life might exist in different environments. They also consider the possibility of detecting biosignatures, which are indicators of past or present life. By piecing together these clues, researchers hope to unravel the mysteries of life beyond our planet, making groundbreaking discoveries about the universe. Hypernovae are incredibly powerful stellar explosions that occur under specific conditions, representing some of the most energetic events in the cosmos. They are typically associated with the deaths of massive stars, those that have a mass exceeding about 30 times that of our Sun. When such a star reaches the end of its life, it exhausts its nuclear fuel, causing its core to collapse under gravity, leading to a cataclysmic supernova. However, if the core's mass is sufficiently great, it can result in an even more violent phenomenon, the hypernova. What sets hypernovae apart from regular supernova is their extraordinary energy output. A hypernova can release energy equivalent to more than 100 times that of a typical supernova. This immense explosion can briefly outshine entire galaxies and can be detected across vast cosmic distances. Hypernovae often eject approximately 10% of the star's mass into space at extremely high velocities, creating shockwaves that can trigger the formation of new stars and influence the surrounding interstellar medium. Another fascinating feature of hypernovae is their potential connection to gamma-ray bursts, which are intense bursts of gamma radiation originating from distant galaxies. These events are believed to occur when a hypernova results in the formation of a rotating black hole. The energy released during this process can produce jets of particles that travel close to the speed of light, creating the observed gamma-ray bursts. Hypernovae significantly enrich the universe with heavy elements such as gold and uranium, forged in the hearts of these dying stars. This elemental contribution is crucial for the chemical evolution of galaxies and the formation of terrestrial planets. Thus, hypernovae do not just mark the end of a star's life, they play a pivotal role in the continuing cycle of stellar birth and death in the universe. Neutron stars represent one of the most extreme forms of matter in the universe, yielding insights that have transformed our understanding of fundamental physics. These remnants of massive stars are incredibly dense, so much so that a sugar cube-sized amount of neutron star material would weigh around the same as an entire mountain on Earth. This extraordinary density arises because, during a supernova explosion, the core collapses, forcing protons and electrons to combine into neutrons and creating a celestial object primarily composed of these subatomic particles. The study of neutron stars has provided an invaluable laboratory for testing theories of fundamental physics under conditions that are impossible to replicate on Earth. For instance, the behavior of matter at such high densities challenges our understanding of quantum mechanics and nuclear physics. Observations of neutron star collisions have confirmed predictions about gravitational waves, which were theorized by Albert Einstein over a century ago, offering proof that the fabric of space-time can become distorted by massive objects moving through it. Additionally, pulsars, a type of rotating neutron star, emit regular beams of radiation that sweep across the sky as the star spins. These rotating neutron stars serve as precise cosmic clocks, allowing researchers to explore the effects of gravity on time, challenge current models of gravity, and even search for evidence of new physics beyond the standard model. The consistency of their pulse rates offers insights into the gravitational forces at play, pushing the boundaries of what we know about astrophysical phenomena. As scientists continue to study neutron stars, including using observatories equipped to detect electromagnetic radiation and gravitational waves, the implications for astrophysics and fundamental physics will keep growing. This research not only helps answer questions about the origins and evolution of the universe, but also has the potential to reveal new realms of knowledge about the underlying principles that govern matter and energy in all forms. Studying the rotation curves of galaxies provides crucial insights into the structure and behavior of these vast cosmic entities. A rotation curve graphs the orbital velocity of stars and gas within a galaxy against their distance from the galaxy's center. As we observe these curves, we notice that the expected velocities based on visible mass do not align with what is actually measured. Instead of following a predictable decline, many galaxies exhibit flat rotation curves, indicating that objects far from the center move at unexpectedly high speeds. This disparity between predicted and observed velocities points to the presence of unseen mass, leading to the conception of dark matter. While galaxies contain significant visible matter in the form of stars, gas, and dust, the rotation curves suggest that this mass only accounts for a small fraction of the total mass. The bulk of a galaxy's mass appears to be composed of dark matter, a mysterious substance that does not emit, absorb, or reflect light, making it invisible. Scientists estimate that dark matter constitutes approximately 85% of the total mass of the universe, fundamentally altering our understanding of cosmic composition. Furthermore, analyzing rotation curves helps astronomers map the distribution of dark matter within galaxies. The shape of the rotation curve provides clues about how this elusive material is spread out, often suggesting that dark matter forms a halo surrounding galaxies. This halo explains not only the stability of galaxies over cosmic timescales, but also their formation and evolution. The study of rotation curves also enhances our understanding of galaxy dynamics, including interactions and mergers between galaxies. Observations reveal that during such encounters, the gravitational forces alter the way galaxies rotate and can trigger phenomena like star formation or the creation of new spiral structures. Therefore, analyzing galaxy rotation curves allows scientists to piece together the intricate puzzle of cosmic evolution, expanding our grasp of the universe and our place within it. The galactic halo plays a critical role in our understanding of the Milky Way galaxy. This vast spherical region extends well beyond the visible disk of stars, encompassing a blend of dark matter, gas, and ancient star clusters known as globular clusters. The significance lies in its influence on the structure and dynamics of the galaxy, influencing the orbits of stars and the overall gravitational field. One of the key mysteries of the galactic halo revolves around dark matter. It is hypothesized that a majority of the halo's mass is made up of this elusive substance that does not emit or absorb light. While scientists have not yet directly detected dark matter, its presence is inferred from the rotation curves of galaxies, showing that stars in the outskirts orbit faster than expected if only visible matter were present. This suggests an unseen mass within the halo, sparking intense research and debates about its nature and properties. Additionally, the galactic halo holds clues to the formation and evolution of the Milky Way. The existence of ancient star clusters within the halo provides insights into the early phases of galaxy formation. These clusters, some of which contain stars that are nearly as old as the universe itself, help astronomers piece together the events that led to the current structure of our galaxy. Understanding these star clusters can reveal how our galaxy interacted with smaller galaxies in the past and contributed to its present state. Moreover, ongoing surveys and advancements in technology have revealed enigmatic bursts of gamma rays and cosmic rays originating from the halo, hinting at the complex processes taking place within this region. These phenomena could be tied to interactions between dark matter and regular matter, possibly unlocking new theories about the universe's composition. Each new discovery adds layers to the mysteries within the galactic halo, inviting continued exploration and research in the quest to understand our place in the cosmos. Globular clusters are dense collections of ancient stars, and their formation involves several fascinating factors. One of the primary contributors is the environment in which they develop. Globular clusters typically form in the gravitational fields of galaxies, particularly in their halos, where they experience both high density and a significant amount of dark matter. This dark matter plays a critical role by providing the necessary gravitational pull to hold these clusters together once they are formed. Another important aspect involves the conditions present in the early universe. These clusters are some of the oldest structures, often containing stars that are nearly as old as the universe itself. The first stars formed after the Big Bang created the initial conditions for globular clusters. They likely coalesced from gas and dust that was enriched by earlier generations of stars, which contributed heavy elements necessary for star formation and the subsequent clustering of those stars. Furthermore, the merger of smaller galaxies is also a contributing factor to the formation of globular clusters. When galaxies collide, they can bring together various star systems, leading to the gravitational binding of stars in tight clusters. These events do not only create new globular clusters, but can also disrupt existing ones, leading to an ever-changing landscape in surrounding cosmic structures. Additionally, The dynamical interactions among stars within these clusters can lead to the formation of tighter groups. Over time, gravitational encounters can generate more compact configurations, resulting in the dense environments that characterize globular clusters today. This complex interplay of large-scale cosmic events and minute stellar interactions creates the rich tapestry of globular clusters scattered throughout galaxies. Time dilation occurs due to the influence of gravity on the flow of time, a concept rooted in Albert Einstein's theory of general relativity. When an object is situated near a massive celestial body, such as a planet or a star, the gravitational field becomes stronger. This strong gravity effectively slows down the passage of time for that object relative to an observer who is farther away from the gravitational source. For example, if a clock is placed near a black hole compared to a clock that is far away from any massive object, the clock closer to the black hole will tick more slowly. This means that while a few hours might pass near the black hole, much more time could elapse for someone observing from a safe distance. This phenomenon has been experimentally confirmed using precise atomic clocks, which have shown that time moves differently depending on the strength of the gravitational field in which they are located. This realization dramatically alters our understanding of time as a constant universal measure. Instead, time is revealed to be relative, tied intimately to the interplay of mass and space-time geometry. It challenges traditional views of time as merely a steady march, and instead portrays it as a more flexible and dynamic dimension influenced by various factors in the universe. By grasping the implications of time dilation, we gain profound insights into not just the nature of time itself, but also into how we perceive the universe around us. It has significant consequences for astrophysics, cosmology, and even our understanding of events like time travel, helping us see the fabric of reality as an interconnected web where gravity significantly impacts the passage of time. Scientists exploring the tantalizing concept of time travel are examining it from several different angles within the framework of advanced physics. One prominent approach involves the theories of relativity proposed by Albert Einstein. His general theory of relativity suggests that massive objects can warp the fabric of space-time, which opens up intriguing possibilities for bending time, theoretically allowing for travel to the past or future in specific conditions. Another avenue of research delves into the notion of wormholes, which are hypothetical passages through space-time that connect distant points in both space and time. These cosmic shortcuts, if they could exist and be stabilized, are thought to create a bridge between different moments in time. Scientists are currently investigating whether quantum mechanics could provide a basis for the creation or manipulation of such structures, although no experimental evidence has yet confirmed their existence. The possibility of time travel is not without its paradoxes, which scientists must consider. For instance, the grandfather paradox poses an interesting dilemma. If someone travels back in time and prevents their own grandfather from meeting their grandmother, would they still exist? These kinds of questions challenge our understanding of causality and the fundamental nature of time, making the scientific discourse around time travel multifaceted and complex. Certain researchers are also exploring the idea of time machines based on concepts from quantum physics, such as closed time-like curves, which could theoretically permit a form of time travel. However, these concepts remain largely theoretical and speculative, as they often require conditions and materials far beyond our current technological capabilities. Thus, while the idea of time travel captivates our imagination, much work is still needed in both theoretical and practical realms to determine if it could ever be achieved. Wormholes have captured the imagination of scientists and the general public alike as a potential means of traveling vast distances in space. They are theoretical passages through space-time that could create shortcuts between two distant points in the universe. While they sound like science fiction, the mathematics behind wormholes derives from Albert Einstein's general theory of relativity, which describes how gravity influences the fabric of space and time. Current theories suggest that if wormholes exist, they could allow for rapid interstellar travel. Rather than journeying through conventional space, a spacecraft might enter one end of a wormhole and emerge from its other end, potentially light years away from the starting point. However, creating or stabilizing a wormhole poses significant challenges. The concept typically relies on exotic matter, which would have negative energy density, to keep the wormhole open against the gravitational forces that would otherwise cause it to collapse. As of now, scientific evidence for exotic matter is purely speculative. Furthermore, the nature of time within a wormhole raises intriguing questions. Some theories propose that traveling through a wormhole could allow for time travel, raising paradoxes that challenge our understanding of causality. This intersection of time and space in wormhole theory ignites discussions about the nature of the universe and our place within it, leading to both excitement and caution among physicists and cosmologists. Currently, while wormholes remain a fascinating aspect of theoretical physics, they exist firmly within the realm of speculation. Advancements in our understanding of quantum mechanics, gravity, and the fundamental laws of the universe may one day reveal whether these enigmatic pathways are a distant possibility for humanity's future in space exploration. Until then, they continue to inspire both scientific inquiry and the imagination of those captivated by the mysteries of the cosmos. Cosmic strings are hypothetical one-dimensional topological defects in the fabric of space-time, and their existence is theorized within various models of cosmic evolution. The primary evidence supporting the idea of cosmic strings comes from their predicted gravitational effects on the surrounding universe. Specifically, these distortions could create an impact on the cosmic microwave background radiation, which is the afterglow of the Big Bang. Scientists seek intricate patterns in this radiation that might indicate the presence of such strings. Additionally, the formation of cosmic strings is expected during phase transitions in the early universe, akin to the way certain structures form when water freezes into ice. If cosmic strings did indeed form during these events, they could act as gravitational lenses, bending light from distant objects as it passes near them. This gravitational lensing effect could leave a distinctive mark on the light patterns we observe from far-off galaxies. Current observational data, such as those gathered from satellites designed to study cosmic microwave background radiation, has yet to provide conclusive proof. However, researchers continue to refine their detection methods, hoping to find those subtle distortions that could signify the presence of cosmic strings. The exciting possibility of finding these relics offers profound implications for our understanding of the universe's evolution and structure. Should they be confirmed, cosmic strings would significantly impact space-time, acting like cosmic highways that could warp light and influence the formation of galaxies. Their potential existence invites scientists to rethink the underlying principles governing the cosmos, challenging current models and opening a realm of possibilities concerning the universe's ultimate fate. Measurements of cosmic distances play a crucial role in understanding the expansion of the universe. At the heart of this investigation is the concept of redshift, which occurs when light from distant galaxies shifts toward longer wavelengths as those galaxies move away from us. The farther away a galaxy is, the faster it appears to be receding. By measuring this redshift and correlating it with distance, astronomers can gather vital data that supports the idea of an expanding universe. This expansion was first notably demonstrated by Edwin Hubble in the early 20th century, when he observed that galaxies are moving away from us, and the speed at which they recede correlates with their distance from Earth. This relationship, known as Hubble's law, suggests that the universe has been growing since its inception in what we refer to as the Big Bang. Understanding cosmic distances enables scientists to create a more detailed picture of how this expansion has changed over billions of years. Furthermore, advancements in distance measurement techniques, such as using standard candles like Type Ia supernovae, have refined our understanding of the rate of expansion. These stellar explosions have a consistent brightness that serves as a cosmic yardstick. By comparing their intrinsic brightness to how bright they appear from Earth, astronomers can calculate the distance to the supernova, providing insight into both local and distant parts of the universe. A remarkable implication of these studies is the realization that the expansion of the universe is not just occurring, but is accelerating. The causes of this acceleration have led scientists to propose concepts like dark energy, an unknown force that contributes to the fabric of the universe. As our measurements of cosmic distances become more precise, they not only enhance our knowledge of the immediate universe, but also unlock the mysteries surrounding its ultimate fate. Some of the most breathtaking nebulae observed through telescopes include the Orion Nebula, the Horsehead Nebula, and the Carina Nebula. Each of these cosmic clouds not only enchants with stunning visual displays, but also plays a vital role in the life cycle of stars. The Orion Nebula, located approximately 1,300 light-years from Earth, is one of the brightest nebulae visible to the naked eye. This region is a stellar nursery where new stars are born from the dense clouds of gas and dust. The nebula is about 2 million times the mass of our Sun and contains several young stars that illuminate the surrounding gas, creating a beautiful tapestry of colors. Its significance lies in the study of star formation and the understanding of the processes that lead to the birth of solar systems. The Horsehead Nebula, residing in the constellation of Orion, presents a silhouette that resembles a horse's head against the backdrop of glowing hydrogen gas. This iconic image is not only visually striking, but demonstrates the dynamic interactions of light and matter. The dark cloud of dust highlights regions of star formation and offers insight into the conditions required for new stars to ignite. Observations of this nebula can help astronomers unravel the mysteries of molecular clouds and their role in stellar evolution. The Carina Nebula, one of the largest and brightest nebulae in the southern hemisphere, is a tumultuous region of intense star formation. It is home to some of the most massive stars known, including Eta Carinae, which is a variable star notorious for its dramatic changes in brightness. The Carina Nebula showcases the interplay of energy and matter, as massive stars emit powerful winds that shape their environment. Its study enables scientists to explore the life cycle of stars and the influence of massive stellar explosions, such as supernovae, on galactic evolution. Through these nebulae, we gain a deeper understanding of the universe's workings and the processes that forge the stars that light up our night sky. The life cycle of a star plays a crucial role in shaping our understanding of the universe. Stars are often referred to as the building blocks of galaxies, and their birth, evolution, and eventual demise provide key insights into the chemical and physical processes that govern the cosmos. This life cycle begins with a molecular cloud of gas and dust, where gravitational forces cause material to collapse and form a protostar. This initial phase is fundamental, as it dictates the characteristics of the star and its eventual impact on the surrounding environment. As stars go through different stages, they fuse hydrogen into helium in their cores, releasing immense amounts of energy in the process. This fusion generates the light and heat that support life on planets like Earth. However, not all stars are created equal. Larger stars live fast and die young, often ending their lives in spectacular supernova explosions. These events are crucial because they spread heavy elements into the surrounding space. Elements like carbon, oxygen, and iron, which are essential for the formation of planets and ultimately life, can only be forged in the cores of stars or during their explosive deaths. The remnants of these stars contribute to the cycle of matter in the universe. When stars exhaust their nuclear fuel, they leave behind neutron stars, black holes, or even become white dwarfs, each playing a unique role in galactic evolution. Through these processes, we learn about the origins of elements, the formation of new stars, and the dynamics of galaxies themselves, revealing a continuous cycle of birth and death that characterizes cosmic history. Furthermore, by studying the life cycle of different types of stars, astronomers can estimate the age of galaxies and the universe. The observation of stars at various stages allows scientists to piece together a timeline of cosmic evolution. This understanding reminds us that we are part of an ever-evolving universe, deeply intertwined with the cycles of stars that existed long before our planet came into being. Magnetars are a fascinating type of neutron star, representing one of the most extreme and mysterious celestial objects in the universe. After a massive star exhausts its nuclear fuel and undergoes a supernova explosion, it can collapse into a neutron star, which is primarily composed of tightly packed neutrons. In the case of magnetars, additional processes lead to the development of extraordinarily strong magnetic fields. What sets magnetars apart from regular neutron stars is their magnetic field strength. While a typical neutron star might have a magnetic field of around 1 million times that of Earth, a magnetar's magnetic field can reach levels that are 1,000 trillion times that of Earth. This immense force is the result of the rapid spinning and collapse of the original star, which amplifies the magnetic field through mechanisms described by the dynamo effect. The intense pressure and temperature conditions present during the formation of a magnetar can further contribute to this extraordinary magnetism. The extreme magnetic fields of magnetars have a profound impact on their surroundings, including the behavior of matter nearby. These fields can have significant effects on the fundamental properties of atoms, even influencing their electronic structure. Moreover, magnetars can release bursts of energy known as gamma-ray bursts, resulting from the rearrangement of their magnetic field and leading to spectacular displays of high-energy phenomena. For scientists and researchers, studying magnetars provides critical insights into the fundamental laws of physics and the nature of extreme states of matter. Solar flares are sudden eruptions of energy on the sun's surface that release a massive burst of radiation. When these flares occur, they can have several profound impacts on technology and life on Earth. The energy from a solar flare can interfere with the Earth's magnetic field, leading to geomagnetic storms that can disrupt communication systems, navigation devices, and power grids. These storms can induce currents in power lines, potentially causing widespread blackouts and damage to electrical infrastructure. In addition to affecting our technology, solar flares can pose risks to astronauts and high-altitude pilots. The radiation from these events can be harmful, as it reaches higher altitudes where the atmosphere provides less protection. This has prompted increased monitoring of solar activity by space agencies, ensuring that necessary precautions can be taken when a flare is detected. Surprisingly, solar flares can even influence atmospheric phenomena. For example, these eruptions can lead to the expansion of the Earth's upper atmosphere, which can impact satellite orbits. Satellites may experience increased drag from the denser atmosphere, affecting their trajectories and operational lifetimes. People often marvel at the auroras that result from solar activity. These stunning light displays are caused by charged particles from the sun colliding with Earth's magnetic field and atmosphere. While these natural spectacles are beautiful, the underlying processes remind us of the interconnectedness of solar activity and life on our planet. With the continued advancements in technology, understanding solar flares and their effects is more important than ever for safeguarding our modern way of life. The Dark Ages of the universe refer to a period that followed the Big Bang, lasting from about 400,000 years after its inception to roughly 1 billion years later. During this era, the universe was filled with neutral hydrogen gas, and no stars or galaxies had yet formed. Although scientists have gathered some clues about what occurred during this time, many mysteries still linger, making it a compelling area of research. One significant unknown is the exact nature of the processes that led to the formation of the first stars, known as Population 3 stars. These stars were crucial in transitioning the universe out of the Dark Ages by producing light and heavy elements. However, their characteristics remain a topic of debate. We have yet to detect any remnants of these stars directly, leaving questions about their mass, temperature, and lifespan unanswered. Thus, while the birth of stars marks the end of this dark period, how it unfolded is still not fully understood. Another enigma involves the density fluctuations in the universe and how they contributed to the formation of the first galaxies. The cosmic microwave background radiation offers a glimpse into the universe's early state and hints at these fluctuations. However, the exact mechanisms by which regions of higher density evolved into the complex structures we observe today are still open to scrutiny. Determining the specifics of this transformation is critical for piecing together the universe's history. Furthermore, there are questions surrounding the reionization era, which occurred shortly after the Dark Ages. This period involved the ionization of hydrogen gas, making it more permeable to light. Understanding when and how this reionization happened is essential for grasping the cosmic timeline. Learning more about it could provide insights into the contributions made by the first galaxies, their feeding processes, and the interplay of dark matter and energy during this transition, revealing more about our universe's extraordinary and intricate narrative. Sending probes beyond our solar system presents a multitude of challenges that stretch the limits of our engineering and scientific understanding. One of the primary issues is the vast distances involved. The closest star system to Earth, Alpha Centauri, is more than 4 light-years away, meaning that light itself takes over 4 years to travel that distance. Current spacecraft, such as Voyager 1, travel at a speed of about 60,000 kilometers per hour. At this rate, it would take tens of thousands of years to reach even the nearest stars. Energy requirements pose another significant hurdle. Probes need a reliable power source for such extensive missions. While solar panels work well within our solar system, they become less effective as they move farther from the Sun. Most probes would likely rely on radioisotope thermoelectric generators, which convert heat from radioactive decay into electricity. However, the availability of suitable radioactive materials limits how far and how well we can power these distant missions. Communication is yet another critical challenge. As probes venture into interstellar space, the vast distances create time delays for the signals we send and receive. A message from a probe 1 light-year away takes 1 year to reach us, and the same goes for our instructions sent back to the probe. This delay complicates real-time operation and may necessitate a high degree of autonomy for the spacecraft. The hostile environment of deep space adds to the complexity of these missions. Probes must be designed to withstand extreme temperatures, intense radiation, and micrometeoroid impacts, all of which can damage delicate instruments. Developing materials and technologies that can endure such conditions is essential for the success of long-duration space missions. As we strive to expand our reach into the cosmos, these challenges serve as a reminder of the complexities involved in exploring realms well beyond our home planet. Light sails, an innovative technology harnessing the momentum of photons, represent a groundbreaking advancement in the realm of space exploration. This method utilizes large, reflective surfaces to capture sunlight, which exerts pressure on the sail, propelling spacecraft forward. The most captivating aspect is that light sails can achieve high speeds without the need for traditional fuel sources. This capability allows for missions to distant celestial bodies or even interstellar travel, where conventional propulsion would be insufficient. The simplicity of light sails extends to their construction. They are often made from lightweight materials, such as mylar or other advanced composites, which enable them to be deployed and maneuver with remarkable efficiency. By harnessing a continuous source of energy, these sails could theoretically maintain acceleration indefinitely, opening up possibilities for reaching areas of our solar system and beyond at a fraction of the time required by current technologies. Moreover, the use of light sails could revolutionize our approach to exploratory missions. By converting light pressure into kinetic energy, missions could be designed to travel to the outer planets and beyond, without the logistical challenges and costs associated with carrying large quantities of propellant. This can lead to smaller, more cost-effective spacecraft that can carry sophisticated scientific instruments, increasing our capabilities to gather data from previously unreachable locations. As these technologies advance, concepts like interstellar probes become more tangible. Scientists envision missions that could reach neighboring star systems within a few decades instead of centuries. This paradigm shift in propulsion can drive humanity's quest for knowledge and exploration, fueling our ambitions to understand the universe and perhaps find new worlds ripe for discovery. The search for habitable moons within our solar system is driven by several scientific theories and principles that help guide researchers in their quest for environments potentially suitable for life. One of the key theories is the concept of extremophiles, which are organisms known to thrive in extreme conditions on Earth. Discoveries of life forms that exist in scorching heat, frigid temperatures, or high-pressure environments suggest that life could survive in similarly harsh conditions elsewhere in the solar system, including icy moons. Another significant theory comes from the study of planetary habitability, which examines a variety of conditions necessary for life as we understand it. Factors such as the presence of liquid water, temperature range, and energy sources play crucial roles in determining whether a celestial body might support life. For moons like Europa, Enceladus, and Titan, the possibility of subsurface oceans or lakes beneath thick icy crusts opens exciting avenues in this search. The presence of water in any form is often considered a fundamental criterion for habitability. Astrobiology also plays a vital role in this search, blending aspects of biology, chemistry, and planetary science. Researchers speculate about the chemical processes that might support life beyond Earth. For instance, the potential for life to utilize chemical energy from the oceanic hydrothermal vents on these moons is particularly intriguing. This perspective broadens the horizons beyond traditional reliance on sunlight, allowing scientists to explore alternative ecosystems that may not resemble Earth's surface life. The study of atmospheric conditions and potential geological activity further contributes to identifying habitable moons. Moons that exhibit geological processes, such as volcanic activity or tectonics, might recycle essential materials and provide energy crucial for sustaining life. Furthermore, missions to investigate these moons aim to gather detailed data on their conditions, significantly guiding our understanding of where life might exist within our own solar system. Through these scientific frameworks, researchers continue to unravel the complex tapestry of possibilities for finding life beyond our planet. Gravitational assists, also known as gravity assists or slingshot maneuvers, are a clever technique used in space exploration to boost the speed and trajectory of spacecraft. By flying close to a planet or another large celestial body, a spacecraft can harness the planet's gravity to gain additional velocity without using extra fuel. This method takes advantage of the complex interplay of motion and gravity, allowing the spacecraft to gain energy from the planetary body as it swings by. Utilizing gravitational assists can significantly expand our range of exploration. For instance, when a spacecraft approaches a giant planet like Jupiter, it can accelerate dramatically by entering its gravitational field at just the right angle and speed. This increase in speed can propel missions farther into space, allowing us to reach destinations like the outer planets, their moons, or even the edges of our solar system more efficiently and cost-effectively. Examples of successful missions employing this technique are plentiful. The Voyager spacecraft series utilized gravitational assists to travel through the entire solar system, visiting multiple planets and revealing invaluable data about them. Similarly, the New Horizons mission, which famously flew by Pluto, conducted a gravitational assist from Jupiter. This allowed it to arrive at its destination much faster than it would have managed relying solely on its propulsion systems. As we look to the future of space exploration, leveraging gravitational assists can help us achieve ambitious goals, such as landings on distant moons of gas giants or even interstellar missions. By carefully planning flight paths, mission designers can maximize the potential of these maneuvers, ensuring that our exploration of the cosmos continues to push boundaries, uncovering secrets that were once thought unreachable. Over the next decade, several remarkable human missions are on the horizon, showcasing humanity's relentless pursuit of exploration. Among these, the most notable is the Artemis program, which aims to return humans to the moon. This initiative plans to land astronauts on the lunar South Pole by the year 2025. The mission will not only search for water ice, but will also establish a sustainable human presence on the moon by the end of the decade. This serves as a critical stepping stone for future missions to Mars. Another ambitious undertaking is the planned crewed missions to Mars, which are being developed by various space agencies and private companies. NASA's ambitious timeline aims for a manned Mars mission by the late 1930s. This mission would focus on investigating the planet's potential for life and understanding its geological history. Private companies such as SpaceX have also set their sights on Mars, proposing to send humans there even sooner. The technological advancements required for these missions challenge our ingenuity and push the boundaries of current space travel. Moreover, the international collaboration around the Lunar Gateway presents an exciting prospect. This space station, orbiting the Moon, will serve as a staging point for lunar exploration and pave the way for deep space missions. It will provide astronauts with a platform to conduct research and experiments in a unique environment, further preparation for eventual journeys to Mars. As scientists and engineers work diligently on these projects, they are also laying the groundwork for broader exploration beyond our immediate solar system. The ambitious plans hint at a future where humanity may not just visit other worlds, but may eventually inhabit them. The next decade promises to be a period of monumental advancements in space exploration, redefining what is possible for humankind in the cosmos. Life as we know it depends on several critical conditions. These include the presence of liquid water, a stable source of energy, an appropriate atmospheric composition, and essential chemical elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Liquid water is particularly important because it serves as a solvent, facilitating chemical reactions essential for life. Energy sources such as sunlight or geothermal heat are also key for sustaining life forms. Plants, for example, utilize sunlight through photosynthesis, while some organisms rely on thermal vents on the ocean floor. The atmosphere plays a vital role as well. It protects organisms from harmful radiation and helps regulate temperature. An atmosphere rich in oxygen and carbon dioxide promotes respiration and photosynthesis, which are fundamental processes for most life on Earth. When considering other planets, these conditions help scientists determine the potential for extraterrestrial life. Mars, for instance, has been a focal point due to evidence of past water flow and signs of ancient riverbeds. Meanwhile, moons like Europa and Enceladus present intriguing possibilities. Both are thought to harbor subsurface oceans beneath icy crusts, which could preserve conditions suitable for life. Astrobiologists also examine exoplanets, planets outside our solar system, for potentially habitable environments. The search focuses on planets located in the so-called Goldilocks zone, where conditions might be just right for liquid water to exist. Instruments like space telescopes are continually improving our ability to detect these distant worlds and assess their potential to support life as we understand it. Extremophiles are remarkable organisms that thrive in conditions once thought to be inhospitable to life. By surviving and even flourishing in environments with extreme temperatures, pressures, acidity, or salinity, these creatures expand our understanding of the potential for life beyond our planet. For instance, some extremophiles can endure environments around hydrothermal vents on the ocean floor, where temperatures can reach several hundred degrees Celsius, demonstrating that life does not require the mild conditions we often associate with habitability. The study of extremophiles reveals that life is incredibly adaptable. This adaptability suggests that, rather than limiting the search for extraterrestrial life to Earth-like conditions, we should explore a wider range of environments elsewhere in the universe. For example, the presence of water beneath the icy crust of moons like Europa and Enceladus prompts astrobiologists to consider the possibility of microbial life thriving in such frigid, dark worlds. The extremophiles on Earth serve as a tangible model for scientists to understand what life might look like in these alien environments. Furthermore, extremophiles can provide insights into biochemistry that differs from the norm. Many rely on unique metabolic pathways that utilize chemical energies from the environment, which include processes not dependent on sunlight or oxygen. This expands our view of what constitutes a viable habitat, allowing for the inclusion of worlds with different elemental compositions or atmospheres. The findings from extremophile research can therefore guide missions to other planets or moons, directing them to sites where life could potentially exist under extreme conditions. Lastly, the resilience of extremophiles fuels the imagination regarding the possibilities for life's evolution. If life can emerge and persist in Earth's harshest places, the probability increases that similar life forms could evolve on other planets with extreme conditions. This broadens the horizons of astrobiology, inspiring scientists to pursue places previously overlooked, all because of what we understand from life thriving on Earth in extraordinary environments. Recent discoveries in our solar system have opened exciting possibilities that could redefine how we search for extraterrestrial life. One of the most compelling locations is Europa, one of Jupiter's moons, which is believed to harbor a vast ocean beneath its icy crust. Data from the Galileo spacecraft and more recent observations have indicated that this subsurface ocean could contain more than double the amount of water found on Earth. The presence of liquid water, coupled with the potential for chemical reactions similar to those on our own planet, raises the intriguing possibility that microbial life may exist there. Another noteworthy contender in the quest for life is Enceladus, a moon of Saturn known for its geysers that eject plumes of water vapor and organic molecules into space. The Cassini spacecraft detected these plumes, hinting at a subsurface ocean. The chemical analysis revealed compounds like simple organic molecules, which are crucial building blocks for life. These discoveries spark speculation about microbial ecosystems thriving in their hidden oceans, similar to those found around hydrothermal vents on Earth. Mars continues to be a focal point in the search for life as well. Evidence of ancient river valleys and lake beds suggests that liquid water once flowed on its surface. Furthermore, the recent discovery of seasonal dark streaks, known as recurring slope lunar, indicates potential briny liquid water may still exist. Recent missions have also found organic molecules in Martian soil, expanding the likelihood that life could have existed there in the past, or even that some form of life might persist now, possibly dormant beneath the surface. Beyond these moons and planets, our understanding of life may change dramatically if we uncover extremophiles, organisms on Earth that survive in extreme conditions, such as high radiation, extreme temperatures, and acidity. These discoveries challenge our preconceived notions of where and how life could exist. As technology advances, missions focused on environments previously deemed uninhabitable may yield remarkable results, pushing the boundaries of our understanding of life's adaptability and presence throughout the solar system. Understanding ribonucleic acid, or RNA, plays a significant role in our quest to find extraterrestrial life. RNA is a critical molecule in the biology of Earth, acting as a messenger that carries genetic information from DNA to the machinery that synthesizes proteins. This fundamental role suggests that any life form, alien or otherwise, could potentially share similar biochemical processes. One fascinating aspect of RNA is its ability to exist in various forms and perform multiple functions. Some researchers theorize that an RNA world could have existed before the emergence of DNA-based life. If this hypothesis holds, it stands to reason that extraterrestrial life may also utilize RNA as an essential component. By identifying environments in space where RNA could form, scientists can better target places to search for signs of life. The search for extraterrestrial RNA also expands our understanding of what constitutes life. Scientists are actively exploring how alternative biochemistries, such as those based on different elements or compounds, might support life in extreme environments. Discovering non-carbon-based analogues of RNA could redefine our idea of habitability beyond traditional Earth-like planets, allowing for a broader range of life forms that could exist elsewhere. Moreover, missions to Mars and the icy moons of Jupiter and Saturn often include experiments specifically designed to detect nucleic acids, or their building blocks. By simulating extraterrestrial conditions in laboratories and analyzing samples from other celestial bodies, researchers aim to unveil the presence of RNA, which could be a crucial indicator of past or present life. The implications of these discoveries could reshape our understanding of life's origins, not only on our planet, but across the cosmos. When searching for signs of life in our solar system, several intriguing locations come to the forefront. Mars often attracts significant attention due to its history of liquid water and evidence suggesting that it once had a more hospitable climate. Recent missions have uncovered ancient riverbeds, lake deposits, and even subsurface ice, hinting at the planet's potential to harbor microbial life in the past, or even today. The possibility of finding microbial life in protected niches beneath the surface makes Mars a prime candidate in our quest for extraterrestrial organisms. Another exciting contender is Europa, one of Jupiter's moons. Beneath its icy crust lies a vast ocean of liquid water, potentially in contact with the moon's rocky mantle. This environment could offer the necessary chemical reactions for life. Scientists believe that plumes of water vapor erupting from the surface may provide a direct route to study its subsurface ocean, making Europa a key target for future missions aimed at detecting signs of life. Enceladus, one of Saturn's moons, is also noteworthy. Like Europa, it boasts a subsurface ocean beneath a thick layer of ice. Observations from the Cassini spacecraft revealed geysers that spew water vapor and organic molecules into space. The presence of these building blocks of life in its plumes suggests a potentially habitable environment beneath its icy shell. This propelled Enceladus into the spotlight as a significant prospect for finding biological signs. Finally, Titan, Saturn's largest moon, challenges our traditional notions of habitability. It possesses lakes and rivers of liquid methane and ethane, alongside a thick atmosphere rich in organic compounds. While its conditions differ vastly from those on Earth, Titan's complex chemistry raises the possibility that life could exist in forms unimagined, existing in a liquid environment entirely different from water. Each of these locations allows us to expand our understanding of where life could thrive, igniting our curiosity about the possibilities that await us in the cosmos. The Voyager missions, which launched in the late 1970s, provided groundbreaking insights into our outer solar system. As Voyager 1 and Voyager 2 traversed toward the outer planets, they delivered a wealth of data about the gas giants and their many moons. Both spacecraft were equipped with instruments designed to capture images, analyze atmospheric compositions, and measure magnetic fields, which significantly expanded our understanding of these distant worlds. One of the most remarkable discoveries involved the intricate and dynamic atmospheres of Jupiter and Saturn. Voyager revealed Jupiter's Great Red Spot, a colossal storm larger than Earth that had been swirling for centuries, demonstrating the planet's complex meteorological patterns. Notably, Voyager also uncovered the existence of faint ring systems around both Jupiter and Saturn, providing evidence that these majestic planets are not just giants, but also possess their own unique and intricate satellite systems. The missions also shed light on the moons of these planets. For instance, Voyager 2's flyby of Uranus unveiled a world with an unusual tilt and dark rings that were previously unknown to scientists. The revelations about Triton, Neptune's largest moon, were equally surprising. Its geysers suggested the presence of subsurface activity, hinting at a more complex geologic history than previously considered. Furthermore, these missions deepened our knowledge of the magnetic fields surrounding these planets. Voyager's findings indicated that magnetic fields interact in intricate ways with their respective environments, unveiling phenomena that defined planetary atmospheres. The data gathered by the Voyager spacecraft have continued to fuel research and inspire future explorations of these enigmatic outer realms, providing a clearer picture of our solar system's complexity. The Mars rovers have significantly transformed our understanding of the red planet and its potential to harbor life. When these robotic pioneers, such as Spirit, Opportunity, Curiosity, and Perseverance began their missions, they were equipped with sophisticated scientific instruments designed to analyze soil, rock, and atmosphere. Their findings indicated that Mars was not always the barren landscape we see today. It once had conditions suitable for life. Discoveries made by the rovers revealed evidence of ancient riverbeds, lakes, and minerals like clay, which typically form in the presence of water. For instance, Curiosity found various geological formations that hinted at long-gone bodies of water, suggesting that microbial life could have existed in those environments billions of years ago. These revelations challenged the long-held belief that Mars was completely inhospitable and opened up new possibilities regarding the planet's history and its potential to support life. Beyond examining the geology, the rovers also performed in situ analyses to detect organic molecules, the building blocks of life. Organic compounds, while not definitive proof of life, hint at the chemical processes that could support life forms, past or present. Perseverance, for example, is specifically tasked with seeking signs of ancient life and collecting samples that may one day be returned to Earth for detailed analysis, furthering our quest to understand the planet's habitability. The findings from the rovers have prompted scientists to reconsider where and how we search for life beyond our planet. As a result, Mars is now regarded as a prime candidate for understanding the potential for life elsewhere in the universe. These missions have ignited interest and exciting debates in the scientific community, reshaping our perspective not only on Mars, but also on the nature of life itself and its resilience in the universe. The journey of space probes has provided invaluable lessons that continue to shape space exploration. Each mission, whether a triumph or a setback, adds to our understanding of technology, science, and the challenges of venturing into the unknown. For instance, the success of the Voyager missions taught us not only about the outer planets, but also about the importance of robust engineering in enduring harsh environments. Voyager's ability to communicate over vast distances inspired improvements in long-range communication systems still relevant today. Conversely, failures like the Mars Climate Orbiter emphasize the need for rigorous testing and standardization. A simple mistake, in this case a misunderstanding between metric and imperial measurements, led to the probe's demise. This incident reinforced the importance of clear communication within teams and rigorous checks in mission planning. Such lessons have dictated better organizational protocols and grounded the practices used in subsequent missions. The triumph of the Hubble Space Telescope showed us that even setbacks could lead to incredible achievements. Hubble initially launched with flawed optics, a disappointment that led to human intervention. The subsequent repairs transformed Hubble into one of the most important scientific instruments, revealing the depths of the universe and enhancing our understanding of cosmic phenomena. This story illustrates the potential for recovery and innovation after failure, reminding us that perseverance can lead to astonishing outcomes. Overall, these experiences forge a culture of meticulous planning, flexibility in problem-solving, and a commitment to collaboration in future explorations. Each success and each misstep lays the foundation for future endeavors, continuing to broaden our horizons and deepen our quest for knowledge about the universe. The Apollo missions fundamentally transformed our understanding of human space exploration by providing a wealth of information about the Moon, advancing technology, and redefining what was possible for humankind. Prior to Apollo, space exploration was largely theoretical, with human capability confined to low Earth orbit. The success of these missions demonstrated that humans could travel beyond our planet, survive in the harsh environment of space, and return safely. With the launch of Apollo 11, astronauts landed on the lunar Sea of Tranquility on July 20, 1969. The experience of astronauts Neil Armstrong and Buzz Aldrin brought not only scientific insights but also a profound psychological impact on both the explorers and the world watching from home. Samples of lunar rock and soil brought back to Earth have provided invaluable information about the Moon's composition, formation, and geological history. These findings significantly advanced our knowledge of planetary science and the evolution of our solar system. The technological advancements spurred by the Apollo program were equally substantial. The development of life support systems, navigation technologies, and even materials like heat shields played a crucial role in not only supporting lunar missions, but also laying the groundwork for future endeavors, including the Space Shuttle program and the International Space Station. The engineering challenges overcome during Apollo inspired generations of scientists and engineers, emphasizing the power of innovation when humanity comes together to solve complex problems. Moreover, the Apollo missions redefined international cooperation and competition in space. The Cold War backdrop framed these missions not just as national achievements, but as pivotal moments in the ongoing narrative of human ambition and exploration. With their legacy, the Apollo missions have ignited ongoing interest in space, paving the way for future missions to Mars and beyond, ensuring that our quest for knowledge and exploration continues to grow. The discovery of exoplanets by the Kepler Space Telescope fundamentally transformed our understanding of the universe. Before Kepler, the existence of planets beyond our solar system was a subject of speculation and limited evidence, with only a handful of candidates identified. Kepler's mission, which launched in 2009, equipped astronomers with the tools to detect these distant worlds systematically. It used the transit method, observing the dip in brightness of stars as planets passed in front of them, to identify thousands of new exoplanets. One of the most significant impacts of Kepler's discoveries was the revelation of the astonishing diversity of planetary systems. Scientists found planets that were similar in size to Earth, as well as gas giants much larger than Jupiter. Some planets orbited their stars at distances similar to those of Mercury and Venus from our Sun, which challenged existing theories about planetary formation and migration. This wide variety urged astronomers to reconsider how unique our solar system truly is. Kepler's data has also sparked interest in the search for potentially habitable exoplanets. The mission identified many worlds located in their stars' habitable zones, where liquid water could exist on a planet's surface. This ignited a fervor among scientists and the public alike, as the quest for extraterrestrial life gained momentum. Future missions now aim to study these planets' atmospheres and chemical compositions, hoping to uncover signs of life beyond Earth. The legacy of the Kepler mission is profound, as it laid the groundwork for contemporary astronomy. It expanded the catalogue of known exoplanets to well over 4,000, fostering an entire field of research focused on characterizing these distant worlds. The excitement surrounding exoplanets has transformed how we think about our place in the cosmos and ignited a new age of exploration and discovery in astrobiology and planetary science. Several upcoming telescopes are poised to transform our understanding of the cosmos dramatically. One of the most anticipated is the James Webb Space Telescope, set to launch soon. Unlike its predecessor, the Hubble Space Telescope, which primarily observes invisible light, the James Webb will focus on infrared wavelengths. This capability allows it to peer through cosmic dust clouds, where stars and planets are born, and to observe the light from the earliest galaxies formed after the Big Bang. Its innovative technology is expected to unveil unprecedented details about the formation of stars, planetary systems, and the potential for life beyond Earth. Another significant project is the Extremely Large Telescope, which will be located in the Atacama Desert in Chile. With its mirror spanning a remarkable 39 meters, it will be the largest optical telescope ever built. Home to a host of advanced instruments, this telescope aims to investigate the atmospheres of exoplanets, search for biosignatures, and explore the mysterious nature of dark matter and dark energy. The insights gained from this facility could answer fundamental questions about our universe and our place within it. The Square Kilometre Array is another groundbreaking initiative that holds great promise for radio astronomy. This vast observatory, which will combine thousands of radio antennas across Australia and South Africa, is expected to enhance our understanding of cosmic phenomena such as black holes, neutron stars, and the very fabric of space-time itself. By surveying the universe at unprecedented sensitivity and resolution, this telescope will collect data that could lead to discoveries about the origins of galaxies and the processes driving cosmic evolution. Lastly, the Lunar Gateway, part of a broader endeavor also involving lunar exploration, is anticipated to facilitate a new era of astronomical observations from space. Positioned in orbit around the Moon, it will provide a strategic site for various telescopes that can observe celestial bodies without the interference of Earth's atmosphere. This unique platform will enable scientists to conduct investigations that are currently limited by ground-based observations, offering fresh insights into the dynamics of our universe. Each of these upcoming telescopes contributes to a thrilling frontier in cosmology, where the mysteries of the universe await eager exploration. Artificial intelligence holds significant promise in analyzing the colossal amounts of data produced by astronomical observations. Each year, telescopes and space missions generate an overwhelming volume of information, from images of distant galaxies to spectral data that reveals the chemical composition of celestial bodies. This scale of data is often beyond the capacity of traditional analytical methods, and here is where artificial intelligence steps in. Machine learning algorithms can sift through this data rapidly, identifying patterns and anomalies that might go unnoticed by human researchers. For example, they can detect transient events like supernovae or gravitational waves, which occur for brief moments in the cosmic timeline. AI can enhance image recognition, helping scientists to classify celestial objects, such as differentiating between stars, planets, and galaxies with remarkable accuracy. The ability of artificial intelligence to learn from existing datasets empowers it to refine its predictive capabilities continuously. As more data is fed into these systems, they become better at identifying interesting features and correlations. This not only accelerates research but also opens new avenues for discovery, as AI can suggest hypotheses that scientists may not have considered previously. Projects like the search for extraterrestrial intelligence have also begun utilizing AI to analyze radio signals from space. These types of investigations benefit immensely from AI's capacity to process data in real time, potentially leading to groundbreaking findings about the universe and our place within it. As AI continues to evolve, its role in cosmology will likely expand, driving new discoveries and enhancing our understanding of the cosmos. Scientists are actively developing a range of new technologies to explore asteroids and comets, leading to exciting advancements in our understanding of these celestial bodies. One of the most promising areas of innovation involves advanced spacecraft and instrumentation. For instance, missions like the Double Asteroid Redirection Test have been designed to test planetary defense techniques by altering the trajectory of an asteroid. This mission uses cutting-edge navigation and imaging technologies to observe and analyze its target in unprecedented detail. Another significant advancement is in the realm of remote sensing techniques. Newly developed spectrometers and imaging devices allow scientists to analyze the surface composition of asteroids and comets from great distances. These tools can detect organic molecules and water ice, giving researchers insights into the building blocks of life and the early conditions of our solar system. By utilizing technology that combines infrared and visible light observations, scientists can gather comprehensive information about these bodies' physical properties and evolution. Robotic landers and sample return missions represent another area where technology is progressing rapidly. Missions like Hayabusa and OSIRIS-REx demonstrate this trend, where spacecraft land on a celestial body, collect samples, and bring them back to Earth for analysis. These missions employ sophisticated collection mechanisms and precise landing technologies, allowing them to target specific geological features and gather invaluable data. Looking ahead, the development of small, agile spacecraft known as CubeSats is becoming increasingly popular for asteroid and comet exploration. These compact, cost-effective satellites can be launched as secondary payloads alongside larger missions, expanding our observational capabilities. Their agility allows for quick maneuvers to gather data from various angles, opening up new possibilities for studying the characteristics and behavior of these intriguing objects in our solar system. The next decade holds enormous potential for transforming our understanding of exoplanetary systems. As technology advances, astronomers will gain access to more sophisticated telescopes and instruments. Projects like the James Webb Space Telescope, set to delve deeper into the cosmos, are poised to deliver unprecedented insights into these distant worlds. By directly observing their atmospheres and compositions, scientists will uncover vital clues about their potential habitability. In addition to better observational tools, an abundance of exoplanets is being discovered through innovative methods such as transit photometry and radial velocity techniques. This flood of new data will enhance our statistical understanding of these systems, allowing researchers to discern patterns in planetary formation and migration. As we gather information on a diverse array of planets, from gas giants to rocky Earth-like worlds, our perspective on what constitutes a suitable environment for life will continue to evolve. Another exciting area of exploration will involve studying the surface conditions and weather patterns of these exoplanets. We will be able to analyze the light reflected from their surfaces, revealing details about their geology and chemical makeup. This capability not only expands our knowledge of distant planets, but also prompts re-evaluation of our own solar system. New discoveries may highlight uncommon features in exoplanet systems that contrast sharply with what we observe here. Moreover, the potential for breakthroughs in artificial intelligence and data processing could accelerate the pace at which we analyze exoplanetary data. With powerful algorithms sifting through massive datasets, patterns may emerge that previously went unnoticed. All these advancements could not only provide answers, but further ignite our curiosity about the universe, prompting questions that challenge our understanding of life in the cosmos. Colonizing other planets offers transformative potential for our scientific understanding. Venturing beyond Earth not only allows us to conduct experiments in varied environments, but it also provides a unique opportunity to study how life adapts and evolves in different extraterrestrial contexts. For instance, if humans establish a base on Mars, researchers could closely examine how our biology responds to altered gravity, radiation levels, and atmospheric conditions. This knowledge could have significant implications for medicine and biology on Earth, potentially leading to advancements in how we understand human health. Additionally, establishing a permanent presence on other celestial bodies, such as the Moon or Mars, would enable us to conduct long-term observations of astronomical phenomena without the interference of Earth's atmosphere. This could enhance our comprehension of cosmic events, such as solar flares or meteor showers, leading to profound breakthroughs in astrophysics and helping us refine our models of the universe. The ability to build sophisticated instruments in space would also mean better data collection, which could unravel many of the mysteries surrounding dark matter and dark energy. Moreover, the challenges of sustaining life on another planet would spark innovative technologies to support human survival. Research in fields like life support systems, sustainable agriculture in harsh climates, and planetary engineering could yield solutions with far-reaching effects on Earth, particularly in the context of climate change and resource scarcity. Solving these challenges could inspire a new wave of scientific investigation that focuses on finding sustainable practices and technologies that could be implemented back home. Lastly, the cultural and philosophical implications of colonization cannot be overstated. The act of living elsewhere compels us to consider our place in the universe and what it means to be human. This raised awareness of our responsibilities both to other worlds and to our own can fundamentally shift our scientific priorities and ethical considerations as we grapple with the challenges of interplanetary life. In exploring the cosmos, we simultaneously reflect on our identity and stewardship of the Earth, pushing the boundaries of scientific inquiry and ethical responsibility. Uranus is a fascinating planet, not just because of its distinctive blue-green color or its collection of rings and moons, but also due to its peculiar rotation. The planet rotates on its side with an axial tilt of approximately 98 degrees. This means that as it orbits the Sun, it rolls along its orbit like a giant bowling ball. Several theories attempt to explain this unusual orientation. One prevalent explanation suggests that Uranus experienced violent collisions with other celestial bodies during its formation. These impacts could have been strong enough to tilt the planet dramatically on its axis. The gravitational interactions with other large bodies in the early solar system might have contributed to this displacement, resulting in the extreme axial tilt we observe today. Evidence supporting this idea comes not only from Uranus itself, but also from simulations of the early solar system's dynamics. Another theory proposes the influence of Uranus's moons and its ring system. Even though the gravitational pull of these celestial bodies is significantly less than that of a larger impactor, the cumulative effects of their gravitational interactions might have contributed to the planet's rotation. Over millions of years, these interactions could have nudged Uranus into its current tilted position. Lastly, there are hypotheses suggesting that the tilt may have arisen from the way Uranus formed, rather than from external impacts. If Uranus had a unique formation history involving a dense disk of material from which it formed, this could have led to its distinctive axial tilt. While many ideas have been put forth, the true cause of Uranus's unusual rotation remains an open question in planetary science, captivating astronomers as they continue to seek answers about this enigmatic planet. Planetary rings typically form from the remnants of moons, comets, or asteroids that have ventured too close to a planet and were torn apart by its gravitational forces. This phenomenon occurs within a region known as the Roche limit, where the gravitational pull from the planet becomes stronger than the cohesive forces holding these smaller bodies together. The debris resulting from this disruption can then spread out in a thin band, creating a stunning ring system. The composition of these rings often depends on the materials that constitute the moon or asteroid. Many rings are predominantly formed from ice particles, mixed with dust and rocky debris. This mixture creates the brilliant, shimmering appearance seen in the rings around planets like Saturn. Interestingly, not all ring systems are uniform. Some are densely packed, while others are more diffused, leading to a variety of visual effects. Certain planets display more pronounced rings thanks to their more substantial gravitational forces and closer proximity to debris sources. Gas giants, such as Saturn, Jupiter, Uranus, and Neptune, have the right combination of mass and distance from the asteroid belt, allowing them to capture material and maintain these dynamic structures. Additionally, the lengthy lifespans of these rings are often a result of the continuous replenishment of material as smaller bodies are drawn in and broken apart. The prevalence of rings around these planets highlights the intricate balance between gravity and material composition in our solar system. While the majestic rings of Saturn might be the most famous, studying the rings of other gas giants reveals the diversity and complexity of these celestial phenomena. Each ring system carries with it a rich history of cosmic interactions and planetary evolution. The exploration of Saturn and its moons has revealed numerous unexpected discoveries that have captivated scientists. One of the most surprising findings came from the Cassini-Huygens mission, which entered orbit around Saturn in 2004. Among its most astonishing revelations were the intricate dynamics and features of Saturn's rings, which were more complex than previously believed. The rings were found to host a number of tiny moons, often referred to as moonlets, that influence the shape and structure of the rings, creating gaps and waves that were not anticipated. Enceladus, one of Saturn's largest moons, emerged as a remarkable focal point for scientific curiosity. Cassini discovered plumes of water vapor erupting from its southern polar region, indicating that this icy moon harbors a subsurface ocean. The presence of liquid water beneath its icy crust raised exciting possibilities for hosting microbial life. Analysis of the plumes showed that they contained organic compounds, which added to the intrigue surrounding Enceladus as a candidate for astrobiological studies. Another astonishing find involved Titan, Saturn's largest moon, which features a thick atmosphere and lakes of liquid methane and ethane on its surface. The discovery of methane lakes was unexpected, as scientists anticipated a more barren landscape. This unique environment presents a striking contrast to Earth, compelling researchers to explore the potential for alternative forms of life or chemical reactions that might occur under Titan's frigid conditions. Furthermore, the complexity of Saturn's magnetic field and its interaction with the solar wind provided scientists with unexpected insights into planetary magnetospheres. The findings suggested a more dynamic and intricate relationship between the planet and its surrounding environment than previously thought. Each of these discoveries not only deepened our understanding of Saturn and its moons, but also left researchers with lingering questions about the potential for life elsewhere in our solar system. The Sun is the central star of our solar system and serves as the primary source of light and heat for all the planets that orbit around it. Its immense gravitational pull keeps these planets in their respective orbits, while the energy it emits affects the climates and weather patterns on each world. The intensity of solar radiation varies significantly with the distance from the Sun, leading to drastic differences in climate. For instance, the closer a planet is to the Sun, like Mercury or Venus, the hotter it tends to be due to receiving more solar energy. On Earth, the sun's energy drives atmospheric circulation and ocean currents, fundamental processes that help maintain our climate. The tilt of the Earth's axis causes seasonal changes, as areas receive differing amounts of solar radiation throughout the year. This solar energy is also essential for photosynthesis, the process through which plants convert sunlight into food, thereby sustaining life on our planet. The sun's influence extends beyond just temperature. It impacts wind patterns, precipitation, and even oceanic phenomena like El Niño and La Niña. Alternatively, the outer planets, such as Jupiter and Saturn, receive significantly less solar energy due to their greater distance from the Sun. Consequently, their climates are vastly different from those of the inner planets. For example, Jupiter, although far from the Sun, has a complex atmosphere with powerful storms, including the Great Red Spot, driven by its internal heat rather than solar input. The intricate balance of solar radiation and each planet's distance from the Sun shapes the myriad climates observed across the solar system. Interestingly, the Sun's activity also affects planetary climates. Solar flares and coronal mass ejections can lead to increased solar wind, which interacts with planetary atmospheres, influencing things like auroras and atmospheric stripping, particularly on planets with thin atmospheres. Understanding the Sun's role in our solar system helps us comprehend not just the climates of other planets, but also the long-term patterns that can influence potential life on those worlds. Tides in the ocean are primarily governed by the gravitational pull of celestial bodies, particularly the Moon and the Sun. The Moon's gravitational force is the most significant influence on Earth's tides because it is the closest large body in space. As the Moon orbits the Earth, its gravitational pull creates a bulge in the water on the side of the Earth that faces the Moon. This bulge is what we experience as high tide. In addition to the high tide created by the Moon, there is a second high tide occurring on the opposite side of the Earth. This second bulge is caused by the centrifugal force generated by the Earth-Moon system. As the Earth rotates on its axis, the gravitational pull of the Moon causes the ocean to pull away from the Earth on this far side, creating a tidal bulge there as well. Consequently, most coastal areas experience 2 high tides and 2 low tides each lunar day. The Sun also plays a role in the creation of tides, though its impact is less than that of the Moon due to its greater distance from Earth. When the Earth, Moon, and Sun align during new moons and full moons, the gravitational forces combine to create especially high and low tides, known as spring tides. Conversely, during the first and third quarters of the lunar phase, when the Sun and Moon are at right angles relative to Earth, we experience nap tides, which are lower than average. Understanding these celestial influences helps illuminate the regular rhythmic cycles of tides that have significant effects on marine ecosystems, coastal geography, and even human activities. The dance of gravity between the Earth and its celestial neighbors not only shapes the oceans, but also influences life in myriad interconnected ways. The theory of relativity, developed by Albert Einstein, plays a crucial role in our understanding of cosmic events. This groundbreaking theory is divided into 2 parts: special relativity and general relativity. Special relativity, which deals with objects moving at constant speeds, introduces the idea that the laws of physics are the same for all observers, regardless of their relative motion. One of its key revelations is that the speed of light is the ultimate speed limit in the universe, fundamentally altering how we perceive time and distance. General relativity extends these concepts to include gravity, presenting it not as a force but as a curvature in space-time. Massive objects, such as planets and stars, warp the fabric of space and time around them, causing other objects to follow curved paths. This idea has profound implications for cosmic events, such as the bending of light around massive galaxies, known as gravitational lensing, which allows astronomers to see distant objects that would otherwise be hidden. The theory also helps explain extreme phenomena, such as black holes, which are regions in space-time where gravity is so intense that nothing can escape their pull. As objects approach a black hole, they experience time dilation, meaning time appears to slow down relative to observers far away. This unique effect challenges our intuitive understanding of time and emphasizes the interconnectedness of space and time in the cosmos. Furthermore, general relativity underpins our understanding of the expansion of the universe. It provides the framework for the Big Bang theory and supports the concept of an expanding cosmos where galaxies move away from each other. This expansion is a heady reminder of the ever-changing nature of our universe, governed by the principles established through Einstein's revolutionary insights. Simulations of the universe have become invaluable tools in the field of astrophysics, allowing scientists to create detailed models of cosmic phenomena. These simulations enable researchers to replicate conditions that existed shortly after the Big Bang, observe the formation and evolution of galaxies, and even predict the behavior of cosmic structures over billions of years. When compared with observational data, these simulations often provide a clearer understanding of complex processes, both supporting and at times challenging existing theories. For example, simulations of cosmic structure formation have confirmed many aspects of the cold-dark matter paradigm. This theory posits that dark matter, though not directly observable, constitutes a significant portion of the universe's mass and plays a crucial role in shaping galaxies. When simulations incorporate dark matter, they accurately reproduce the distribution and clustering of galaxies observed in the universe today. These findings bolster the validity of the dark matter hypothesis and highlight its importance in our understanding of cosmic evolution. However, not all simulations align perfectly with observational evidence, leading to crucial discussions and revisions of existing theories. A notable example is the discrepancy between the predicted number of small galaxies formed in simulations and the number detected in studies of the Milky Way and similar galaxies. This inconsistency has prompted scientists to reconsider aspects of galaxy formation and the role of baryonic matter, the ordinary matter that makes up stars and planets, suggesting that our current models may need refinement. This inconsistency has prompted scientists to reconsider aspects of galaxy formation and the role of baryonic matter, the ordinary matter that makes up stars and planets, suggesting that our current models may need refinement. The ongoing interplay between simulation and observation serves as a foundation for scientific progress. When simulations contradict established theories, rather than simply dismissing them, researchers delve deeper into the underlying physics, refining their models and leading to breakthroughs in our understanding of the universe. Each new simulation offers both confirmation and challenge, pushing the boundaries of our knowledge about the cosmos. Models of stellar evolution are undergoing significant transformation due to the discovery of new types of stars that challenge existing theories. Traditional models often centered around well-studied stars like our Sun and the more familiar types we commonly observe. However, recent astronomical advancements have unveiled a diverse array of stellar phenomena, leading to the need for more intricate models that can account for this complexity. One particularly influential discovery has been the identification of peculiar stars, such as blue supergiants and hypergiants, which exhibit properties that defy the classic models. These massive stars burn through their nuclear fuel at astonishing rates, resulting in shorter lifespans and unique evolutionary paths. The inclusion of these extreme cases into models forces astronomers to re-evaluate our understanding of stellar life cycles, particularly in the context of massive star evolution and subsequent supernova events. Additionally, the advent of powerful telescopes and observational techniques has enabled scientists to study previously hidden populations of stars, including those in dense star clusters and exotic environments. These observations reveal that stars can interact in unforeseen ways, such as merging with one another or receiving material from a neighboring star. This necessitates a more dynamic approach to stellar modeling, integrating factors like mass transfer, angular momentum, and the impact of close stellar companions. As new discoveries continue to emerge, the models of stellar evolution are becoming increasingly sophisticated. Researchers are now employing advanced computational simulations to capture the nuances of stellar interactions and the role of cosmic elements in shaping a star's destiny. This evolution in understanding not only broadens our grasp of stellar life cycles, but also enhances our knowledge of the cosmic landscape in which these stars exist, paving the way for new insights into the universe as a whole. The Big Bang theory suggests that our universe began approximately 13.8 billion years ago as an infinitely dense point, rapidly expanding to create space, time, and all the energy that we observe today. This initial expansion set the stage for all future developments in the cosmos. Understanding this beginning allows scientists to infer how the universe might evolve and what its fate could be. As the universe continues to expand, the implications are significant. Current observations show that this expansion is accelerating, primarily driven by a mysterious force known as dark energy. This phenomenon hints that the universe is not merely growing larger, but is doing so at an ever-increasing rate. If this trend continues, the ultimate fate of the universe may lead to a scenario known as the Big Freeze, where galaxies drift apart, stars burn out, and matter becomes increasingly dispersed. Alternatively, there are other potential scenarios rooted in the Big Bang theory. One possibility is the Big Crunch, which revolves around the idea that the expansion could eventually halt and reverse, leading all matter and energy to collapse back into a singularity. This idea, however, relies on different parameters and assumptions about the density and nature of the universe's mass-energy content, which current measurements do not strongly support. Another fascinating theory often discussed is the Big Rip, where the acceleration of the universe pushes every structure apart, eventually tearing galaxies, stars, and even atomic particles asunder. While these ideas may sound speculative, they illustrate how the Big Bang theory not only describes the universe's origin, but also serves as a crucial framework for predicting its distant future. Consequently, the Big Bang theory continues to be central to cosmology, guiding our understanding of the universe's past, present, and what may lie ahead. Different cosmological models offer fascinating predictions about the ultimate fate of the universe, shaped largely by our understanding of its expansion and the fundamental forces at play. The most well-known models are based on general relativity and considerations of the universe's density and energy content. These models revolve around concepts such as the critical density that determines the geometry of space. One significant model is the Big Crunch scenario, which posits that if the density of the universe is greater than the critical density, gravitational forces will eventually halt the expansion and reverse it, leading to a collapse. This would culminate in a singularity, where all matter and energy condense back into a dense state. Conversely, in a model where the universe's density is less than the critical value, the Big Freeze comes into play. This scenario foresees an eternal expansion, leading to a cold, dark, and dilute universe where stars burn out and galaxies drift apart. The role of dark energy introduces more complexity into these predictions. Dark energy, believed to be responsible for the accelerated expansion of the universe, suggests another potential outcome known as the Big Rip. In this model, the repulsive force of dark energy increases over time, tearing apart not just galaxies but also planets and eventually atomic structures themselves. Each of these models illustrates the intricate interplay of gravity, energy, and the structure of the cosmos. These varying predictions emphasize the mysteries still present in our understanding of the universe. As observational technologies and techniques improve, scientists continue to evaluate the universe's behavior, refining these models and exploring the implications of our findings. Each cosmological model does not just represent a static theory, it is a dynamic reflection of our quest to comprehend the cosmos and its ultimate fate. Astronomers have observed several unusual patterns of star formation that defy our traditional understanding of how stars are born. One striking example is the phenomenon of starburst galaxies. These galaxies undergo rapid and intense bursts of star formation, often producing hundreds or even thousands of new stars in a relatively short span of time, sometimes just a few million years. This frenzy can be triggered by events such as galaxy collisions, which compress gas and dust, igniting bursts of star formation. Another fascinating observation involves dense cores within molecular clouds, where conditions are ideal for starbirth. Sometimes these regions form clusters of stars instead of single stars. This process can lead to the creation of whole communities of stars that evolve together, often bound by their mutual gravitational attraction. An exceptional case is the Orion Nebula, where a rich cluster of young stars is forming in a relatively small region, illuminating the surrounding gas and dust in spectacular ways. There are also discoveries of solitary stars forming in isolation, far away from the denser regions of galaxies. These stars seem to arise in the cold interstellar medium where conditions are less favorable for star formation. This finding challenges the idea that all stars must form in clusters and suggests that the universe has many more diverse environments conducive to starbirth than previously thought. Additionally, astronomers have identified what are known as runaway stars. These are stars that form near the dense centers of star clusters, but end up ejected into interstellar space due to gravitational interactions. This leads to a fascinating scenario where a star that began in a thriving stellar nursery ends up shining alone in the vastness of space, far from its birthplace. These unusual patterns illustrate that star formation is a complex and varied process, full of surprises that continue to intrigue scientists exploring the cosmos. The silence of the cosmos can be traced back to the very nature of sound itself. Sound requires a medium such as air or water to propagate through. In the vacuum of space, there are insufficient particles for sound waves to travel, leading to an absence of audible noise. This stark environment leaves us with an almost profound stillness when we look up at the stars. While this silent expanse may seem unsettling, it instills a sense of perspective about our place in the universe. The sheer scale of the cosmos serves as a contrasting backdrop to our everyday existence on Earth. It ignites curiosity, encouraging scientists and enthusiasts alike to contemplate the mysteries that lie beyond our atmosphere, despite the lack of sound. Explorations of the cosmos reveal other ways it can communicate with us. Instead of sound, we detect signals through electromagnetic radiation, such as visible light, radio waves, and gamma rays. Telescopes and instruments on Earth and in space pick up these signals, translating cosmic events into data we can analyze and understand. For instance, when a star explodes in a supernova or a neutron star collides with another, the resulting waves can be measured and decoded, albeit silently. The eerie quietude of space, coupled with the rich tapestry of information encoded in the cosmos, drives humanity's quest for knowledge. Each mission to another planet or satellite sends back more than just images. It provides glimpses into the stories of our universe. So while the cosmos may appear eerily silent, it is anything but without secrets waiting to be uncovered through our scientific endeavors. Throughout history, humanity has kept meticulous records of astronomical events, and these accounts significantly shape our current understanding of the cosmos. Ancient civilizations, such as the Babylonians and the Chinese, documented celestial occurrences like solar eclipses, planetary alignments, and supernovae. Their observations provided invaluable data that helped future generations map the heavens, understand celestial movements, and even predict events with astounding accuracy. One notable example is the supernova recorded by Chinese astronomers in the year 1006. This event, which produced a bright star visible in daylight for several weeks, was documented in detail. Centuries later, when scientists discovered the remnants of this supernova, they realized it was an important marker for understanding stellar evolution and explosions. Such historical records create a bridge between ancient knowledge and contemporary astronomy, enabling scientists to piece together the history of our universe. The historical observations of comets also enhance our understanding of celestial mechanics. The return of Halley's Comet, noted in various cultures across the ages, allowed astronomers to calculate its orbit and determine that it returns roughly every 76 years. These observations showcase a continuity of knowledge spanning millennia, reflecting a collective human endeavor to comprehend the cosmos. Furthermore, the documentation of celestial events has had a profound impact on cultural and religious beliefs. Events such as eclipses were often interpreted as omens or messages from the divine. As we decipher the past through these records, we not only build a clearer picture of the sky, but also witness how deeply intertwined our understanding of the cosmos is with human history and culture. Each record serves as a reminder of our enduring curiosity and the journey toward unraveling the mysteries of the universe. Throughout history, ancient civilizations have left behind artifacts that reveal their deep connection with astronomy. One of the most remarkable examples comes from the ancient Maya. The Mayans constructed sophisticated observatories like the one at Uxmal, which was designed to study celestial events. They meticulously recorded the movements of stars, planets, and comets, creating a calendar system that was surprisingly accurate, with observations guiding agricultural practices and religious ceremonies. Another significant artifact is Stonehenge, located in England. This prehistoric monument, consisting of massive standing stones arranged in a circular format, aligns with key astronomical events. Researchers believe that it was used as a ceremonial site and possibly for observing solstices and lunar events, as its structure suggests a keen understanding of solar cycles. Stonehenge embodies the blending of spirituality and science as ancient peoples sought to comprehend their place in the cosmos. The ancient Greeks made major contributions too, with artifacts such as the Antikythera mechanism, often regarded as the world's first analog computer. Discovered in a shipwreck off the coast of Greece, this intricate device allows historians to infer how ancient Greeks calculated astronomical positions and celestial events with remarkable precision. It also highlights the intellectual curiosity of this era and their desire to connect the heavens to earthly life. Similarly, the ancient Egyptians built the Great Pyramids, which reflect their astronomical knowledge and beliefs. The pyramids are aligned with incredible accuracy to the cardinal points and were likely oriented to align with significant stars and constellations. These connections show their reverence for the cosmos, believing that the stars played a crucial role in the afterlife and the divine order of the universe. Each of these remnants serves as a powerful testament to humanity's long-standing fascination with the skies above. The WOW signal, detected in 1977, remains one of the most intriguing events in the quest for extraterrestrial communication. This strikingly strong radio signal, which lasted for just 72 seconds, has never been explained or detected again, prompting astronomers and scientists to consider the implications of its origins seriously. The signal was unique, coming from a region of space devoid of nearby stars, leading some to speculate about its potential artificial nature. This single event has ignited curiosity and speculation about the existence of intelligent life beyond Earth. Following the WOW signal, researchers have intensified their efforts to listen for similar messages from distant civilizations. Initiatives like the Search for Extraterrestrial Intelligence, often abbreviated as SETI, have expanded their programs, utilizing advanced technology to scan the cosmos for radio waves that may suggest intelligent origins. With the use of high-powered telescopes and sophisticated algorithms, scientists are now able to sift through vast amounts of data in search of signals that could echo the mysterious characteristics of the WOW signal. Notably, the WOW signal serves as a reminder of how fleeting and rare such occurrences might be. The search is not merely a matter of improving technology, but also developing better strategies to interpret data and identify signals among the noise of cosmic background radiation. Researchers aim to reconstruct the conditions under which the WOW signal appeared, examining its frequency and duration to develop targeted searches for signals that could indicate extraterrestrial intelligence. The legacy of the WOW signal continues to inspire not only scientists, but also enthusiasts and the public at large. While it remains a single, enigmatic event, its influence fuels a growing belief that the universe may be teeming with signals waiting to be uncovered. As humanity steps deeper into the cosmic frontier, each advancement in technology or methodology opens new pathways for discovering what messages the universe might hold. The quest to find extraterrestrial life is ongoing, driven by the mystery of that one extraordinary signal that captivated the imagination of many. Recent advancements in propulsion technology are paving the way for the dream of interstellar travel, a quest that has long captured human imagination. Traditional rocket engines operate on the principle of expelling mass to generate thrust, but they are limited by fuel capacity and efficiency, making them inadequate for the vast distances between stars. Innovative concepts are emerging, including ion propulsion systems, which utilize electric fields to accelerate ions, providing a highly efficient mode of propulsion. This technique allows spacecraft to carry less fuel while still achieving significant speeds, making it a viable option for reaching lower orbits or even distant celestial bodies. Another promising avenue is nuclear thermal propulsion. This technology would use nuclear reactions to heat a propellant, producing thrust that is far greater than conventional chemical rockets. This advancement could shorten travel times within our solar system and lay the groundwork for missions beyond, as the increased efficiency offers the potential for greater speeds over extended journeys. Researchers are also exploring nuclear pulse propulsion, which proposes detonating nuclear devices behind a spacecraft to propel it forward. Although still in theoretical stages, this method could hypothetically allow a spacecraft to attain speeds that approach a fraction of the speed of light. One of the most revolutionary concepts is the idea of using light sails for propulsion. A light sail relies on the pressure exerted by photons from a laser or the sun to propel a spacecraft across vast distances. Projects like the Planetary Society's light sail and the proposed Breakthrough Starshot initiative envision small, lightweight probes that could be accelerated to considerable fractions of the speed of light using ground-based or orbital laser arrays. This could potentially open up the stars within a human lifetime, sending probes to neighboring systems like Alpha Centauri. Lastly, research into antimatter propulsion posits the possibility of using antimatter as a fuel source. Antimatter annihilation releases tremendous amounts of energy, which could be harnessed for propulsion. While the production and containment of antimatter remain significant challenges, the prospect fuels scientific curiosity. Each of these advancements holds the promise of transforming our capabilities for deep space exploration, inching us closer to the reality of interstellar travel. Advancements in telescope technology have revolutionized our understanding of the universe by expanding our ability to observe distant objects, effectively allowing us to look back in time. When we gaze at distant celestial bodies, we are seeing them as they were many millions or even billions of years ago due to the finite speed of light. Light from these objects takes time to reach us, so the further away we look, the older the light is. Modern telescopes are equipped with sophisticated instruments that enhance their sensitivity and resolution. Innovations such as adaptive optics enable telescopes to compensate for atmospheric distortions, resulting in clearer images of distant galaxies and stars. Ground-based telescopes have also increased in size and capability, allowing astronomers to capture more light and observe fainter objects. This means they can study celestial phenomena that were previously undetectable with older equipment. Space-based telescopes like the Hubble Space Telescope further overcome atmospheric limitations entirely, providing remarkable clarity and depth of field. By operating above the interference of Earth's atmosphere, these instruments can capture a broader range of wavelengths, including ultraviolet and infrared light. This capability is crucial for observing the early universe, where many astronomical phenomena emit radiation outside the visible spectrum. As telescopes continue to evolve, the future holds even greater promises. Upcoming missions, such as the James Webb Space Telescope, are designed to delve deeper into the cosmos, allowing us to peer back to the era of the first stars and galaxies. With each new advancement, we strip away the layers of time, revealing the history of the universe and deepening our comprehension of cosmic evolution. Recent advancements in data collection and analysis are markedly transforming our comprehension of phenomena in outer space. One of the most significant innovations comes from telescopes equipped with cutting-edge technology. For instance, surveys conducted by large-scale observatories are improving our ability to capture extensive data across multiple wavelengths, including visible light, radio waves, and infrared radiation. These telescopes now employ advanced sensors and imaging techniques that enhance resolution, allowing scientists to detect fainter and more distant objects than ever before. Moreover, sophisticated data analytics techniques, particularly those rooted in artificial intelligence and machine learning, are playing an essential role in this frontier. By processing colossal amounts of data rapidly, these algorithms can identify patterns that may elude traditional methods. For instance, they are being used to sift through vast datasets obtained from astronomical surveys, pinpointing unusual celestial events like supernovae or the presence of exoplanets by analyzing subtle changes in light. This not only speeds up discovery, but also leads to new insights that push the boundaries of what we know about the universe. Another equally vital innovation is the development of space probes and rovers that gather real-time data from other planets and moons within our solar system. These instruments provide invaluable information, such as atmospheric conditions, surface composition, and the presence of water ice. The data transmitted back to Earth plays a crucial role in expanding our understanding of planetary formation and the potential for extraterrestrial life, highlighting the interconnectedness of various space phenomena. As we continue to innovate both in the tools used for data collection and the methodologies for analysis, our grasp of the cosmos becomes more profound. Each breakthrough not only illuminates the mysteries of our universe, but also raises new questions that drive further exploration and discovery, ensuring that the pursuit of knowledge about space remains a dynamic and exciting challenge. Three-dimensional printing technologies are revolutionizing space exploration by providing innovative solutions to some of the unique challenges faced in space missions. One significant advantage is the ability to create parts and tools on demand, reducing the need to launch heavy payloads from Earth. This capability becomes particularly important when considering the high costs associated with transporting materials and equipment into space. By fabricating components on site, missions can become more efficient and adaptable. NASA has already begun using three-dimensional printing in its endeavors. One remarkable application involved the printing of rocket engine components, which can withstand the extreme conditions of space travel. By using this technology, engineers can design parts that are lighter, stronger, and tailored specifically to meet the needs of a given mission. The flexibility of three-dimensional printing allows for rapid prototyping and testing of designs, leading to quicker innovations without the traditional delays associated with manufacturing processes. Additionally, as missions aim for longer durations, such as those to Mars, the ability to produce food and living necessities using three-dimensional printing becomes increasingly valuable. Researchers are exploring ways to use materials readily available on other celestial bodies like lunar or Martian regolith to produce construction materials or even life support systems. This approach not only supports sustainability, but also significantly lowers the dependency on constant supply from Earth. The future of space exploration is likely to see even more advanced iterations of three-dimensional printing technology, potentially enabling astronaut habitats to be constructed on distant worlds and allowing for repairs and modifications to equipment without the need to return to Earth. This transformative technology exemplifies how innovation can enhance our ability to explore, colonize, and thrive beyond our planet. International collaborations play a pivotal role in the advancement of space science by pooling resources, expertise, and technology from various countries. Space exploration is an incredibly complex endeavor that often requires a range of specialized skills and knowledge. By working together, nations can share the financial burdens associated with expensive missions and infrastructure. This collaboration leads to more ambitious projects, as countries are able to leverage each other's strengths and capabilities to push the boundaries of what is scientifically possible. Moreover, international partnerships foster a spirit of shared knowledge and innovation. Through joint missions, scientists and engineers from diverse backgrounds bring unique perspectives that can lead to breakthroughs in research and technology. For instance, the International Space Station is not only a remarkable laboratory in orbit, but also a symbol of what can be achieved when countries unite for the common goal of exploration and discovery. It provides valuable data on human physiology in space, advances in material science, and environmental monitoring, benefiting all participating nations. Additionally, these collaborations have significant implications for policy and diplomacy. They help to establish norms and agreements around the peaceful use of space, enhancing international relations. By engaging in cooperative projects, countries build trust and mutual understanding, which can help mitigate conflicts on Earth. This diplomatic aspect is essential in an era where the number of nations entering the space race is steadily increasing. Ultimately, international collaborations are fundamental in shaping the future of space science. They not only accelerate advancements, but also ensure that the exploration of outer space remains a shared human endeavor, inspiring generations to look beyond our planet and collaborate for the greater good. Space debris poses a significant environmental challenge for future missions in Earth's orbit, as the increasing clutter in this region continues to escalate. This debris consists of defunct satellites, spent rocket stages, and fragments from previous collisions, all of which travel at high velocities. Even a small piece can cause catastrophic damage to operational spacecraft due to the immense speeds involved. The potential consequences of space debris are not merely limited to physical damage. They also threaten critical satellite operations that oversee communications, weather monitoring, and navigation systems. As the risk of collisions increases, the potential for operational disruptions heightens, which may impact services reliant on these satellites. The economic ramifications could be substantial, with countries and companies facing the potential loss of billions of dollars. Moreover, the issue of space debris raises environmental concerns beyond Earth's atmosphere. As debris collides and breaks apart, it contributes to the proliferation of smaller particles, creating a cascading effect known as the Kepler syndrome. This scenario could create an environment where space travel becomes increasingly hazardous, potentially rendering certain orbits unusable for generations. The challenge of mitigating space debris is further complicated by the difficulty of tracking smaller fragments, the limitations of current cleanup technologies, and the need for international collaboration. As we strive to explore deeper into space, the management and reduction of space debris will be critical to ensuring the ongoing viability of our missions and the protection of our shared orbital environment. Space missions have historically acted as catalysts for technological advancement on Earth. The rigorous demands of space exploration often lead to innovative solutions that eventually find their way into everyday life. For instance, the development of materials that can withstand the extreme conditions of space travel has resulted in stronger, lighter, and more durable materials used in a range of industries, from construction to consumer electronics. One significant area of impact is in medical technology. Many of the imaging technologies used today, like magnetic resonance imaging and computed tomography, were refined and improved through research initially conducted for space missions. The necessity to monitor astronaut health in the unforgiving environment of space spurred advancements in telemedicine, which now allows doctors to conduct remote consultations and diagnose patients from far away. Furthermore, the satellite technology developed for space missions has revolutionized numerous aspects of life on Earth. Global positioning systems, or GPS, revolutionize navigation, while satellite data plays an invaluable role in weather forecasting and disaster response. These technologies were perfected in space, where precision and accuracy are vital, and now they have become integral to our daily routines. The insights gained from studying the Earth's atmosphere and environment from space also lead to advancements in climate science and environmental monitoring. Technologies developed to assess the health of distant planets can now be employed to monitor and protect our own planet. This interconnectedness of discoveries highlights how space missions not only elevate our understanding of the universe, but also enrich our lives through practical applications and innovations. As humanity ventures further into space, the importance of sustainability cannot be overstated. The challenges of preserving our home planet extend beyond Earth, urging scientists and engineers to consider how we can explore the cosmos without compromising future opportunities or damaging celestial environments. One of the main strategies being developed is the concept of in situ resource utilization. This approach promotes the use of local materials found on other planets or moons, significantly reducing the need to transport everything from Earth. For instance, using Martian regolith to produce building materials for habitats could decrease both costs and waste. Another key focus is on reducing space debris. which poses a significant risk to satellites, spacecraft, and astronauts. Innovative solutions, including active debris removal technologies, are being designed to clean up historical remnants of space missions. These methods range from nets and harpoons to lasers that can help deorbit defunct satellites, ensuring a safer environment for future missions. By prioritizing ways to manage and mitigate debris, space agencies are recognizing that responsible exploration is essential for sustainability. Additionally, scientists are exploring the potential of propulsion systems that rely on renewable energy sources. Concepts such as solar sails or ion propulsion offer cleaner alternatives to traditional chemical rockets, which can be both costly and environmentally damaging. The aim is to develop technologies that minimize harmful emissions, resulting in a greener approach to reaching not only low Earth orbit, but also deeper space destinations. Education and collaboration among international space agencies and private companies are also fundamental in fostering sustainable practices. By sharing knowledge, resources, and best practices, the global space community can work together to establish standards and agreements. These partnerships can encourage a collective responsibility toward ensuring that space exploration is not just a race for resources or prestige, but a unified effort to responsibly expand our presence in the universe. Taking these steps today lays the groundwork for a sustainable future in space, allowing us to harness the wonders of the cosmos while protecting it for generations to come. Understanding planetary protection is crucial as our missions to explore other worlds expand. This area of study focuses on preventing biological contamination of both the Earth and other celestial bodies. When we send a spacecraft to Mars, Europa, or any other target, we must ensure that we do not inadvertently introduce Earth-based microorganisms that could potentially interfere with the local ecosystems and scientific observations. Protecting these environments not only preserves their unique biological status, but also ensures that we can study them without the confounding effects of terrestrial life. Planetary protection guidelines are classified into different categories based on the likelihood of finding life and the potential for contamination. For instance, missions to Mars, where there is a possibility of subsurface water or past microbial life, require stringent sterilization protocols. Spacecraft materials must be carefully cleaned and sometimes even baked at high temperatures to eliminate any microbes. Similarly, missions to the icy moons of the outer solar system, such as Europa and Enceladus, are designed with strict protocols to avoid contamination, given their potential subsurface oceans and the likelihood they may harbor life. Public interest in these missions is immense. Understanding planetary protection helps us acknowledge the responsibility we bear as we reach out to other worlds. It's not solely about the scientific advancements that may arise from these explorations. It also involves ethical considerations regarding the preservation of other planetary ecosystems. By adhering to these protocols, we foster a sense of stewardship for the universe, ensuring that our quest for knowledge does not come at the expense of discovery or the potential for extraterrestrial life. Our quest for exploration continues to evolve, embracing the complexities of both discovery and caution. As we prepare for future missions, the principles of planetary protection will remain a guiding force, allowing us to balance scientific inquiry with a respect for the delicate balance of life that may exist beyond our own planet. Each mission teaches us valuable lessons about our responsibilities as explorers, pushing the boundaries of our understanding while safeguarding the integrity of the cosmos. Observing other planets offers a unique window into understanding climate change, as we can analyze varying atmospheres, weather patterns, and geological processes that shape different environments. For instance, studying the atmosphere of Venus reveals the extreme greenhouse effect at work. Its thick, toxic clouds trap heat to create surface temperatures exceeding 800 degrees Fahrenheit. This serves as a stark reminder of what unchecked greenhouse gas emissions can lead to on Earth. Mars provides an equally fascinating contrast. Once it had flowing water and a thicker atmosphere, but over time, it underwent drastic changes leading to its current desert-like state. Understanding how Mars transitioned from a potentially habitable planet to its current environment underscores how fragile planetary atmospheres can be. This highlights the importance of sustaining Earth's climate and signals that drastic environmental alterations can happen over relatively short geological timescales. The gas giants, such as Jupiter and Saturn, show us how storms and atmospheric dynamics function on a grand scale. The Great Red Spot on Jupiter is a storm that has persisted for centuries. This indicates not only the resilience of weather patterns, but also the potential for long-lasting climatic phenomena. Studying such systems helps us grasp the complexities of Earth's own weather patterns and how they may change under varying conditions, including those brought on by climate change. By exploring these diverse planetary environments, we gain important insights into the interplay between a planet's atmosphere and its ability to support life. These lessons can guide our efforts in mitigating climate change, informing policies about emissions, and enhancing understanding of the urgent need to act before irreversible changes occur on our own planet.